Right above your head, hidden in the vast darkness of space, there's a cosmic neighborhood packed with bizarre secrets that defy everything we know about the universe. Welcome to the local group, a collection of more than 50 galaxies, including our Milky Way, the Andromeda galaxy, and countless smaller cosmic oddballs. But here's the twist: some of these objects shouldn't exist. Galaxies that vanish, black holes that misbehave, and invisible forces stronger than gravity itself. Today, we're diving into the 50 strangest objects in our galactic backyard, each one a mystery that leaves scientists scratching their heads. Think you know space? Think again, strap in, because by the end of this journey, your view of the cosmos will never be the same. Now let's zoom in on the very first strangeness in our cosmic neighborhood, the Andromeda galaxy. At first glance, this spiral beauty looks like a mirror image of our Milky Way, but peer closer and something unsettling emerges. Andromeda doesn't have just one bright core, it has two. That's right, a double nucleus glowing eerily side by side. What could possibly cause such a bizarre setup? Scientists have two leading theories, and both sound like something straight out of a sci-fi thriller. The first idea suggests that Andromeda once had a dramatic encounter, a violent collision with another galaxy in the distant past. When galaxies merge, their supermassive black holes can spiral toward each other, eventually settling into a cosmic dance. In this scenario, one of those black holes might have stalled, creating a second bright clump of stars around it. Imagine two giants circling each other, trapped in a gravitational standoff. But here's where it gets weirder. The second theory proposes that Andromeda's double core isn't due to a collision at all. Instead, it might just be one supermassive black hole with a disk of stars orbiting it in a lopsided, elongated path. From our viewpoint, those densely packed stars could appear as two distinct bright spots, even though they're actually part of the same system. It's like watching a glowing hula hoop. Edge on some parts look brighter, some dimmer, tricking us into seeing double. Hubble Space Telescope images have been crucial in this cosmic detective work. They've captured Andromeda's heart in stunning detail, revealing the intricate motions of stars swirling around these mysterious cores. Yet despite the data, astronomers still can't say for certain which explanation is correct. What we do know is that this double nucleus challenges our understanding of how galaxies evolve. If collisions are to blame, it reshapes our view of how often galaxies smash into each other. If it's just an optical illusion, it forces us to rethink how black holes influence their surroundings. Andromeda's strange duality is a perfect example of how even the most familiar cosmic objects can hide jaw-dropping secrets. It's not just a pretty spiral, it's a puzzle, one that keeps rewriting the rules of galactic behavior. So next time you look up at that faint smudge in the night sky, remember, you're staring at a galaxy with a split personality, a cosmic oddity that refuses to play by the book. And if this is just the first object on our list, imagine what other mind-bending surprises are waiting in the local group. Speaking of surprises, let's move on to another head-scratcher, the Triangulum galaxy, where an entire ingredient of the universe seems to have gone missing. Now let's turn our attention to another cosmic oddity lurking just beyond Andromeda, the Triangulum galaxy. On the surface, this spiral galaxy looks perfectly ordinary, a swirling disk of stars and gas much like our own Milky Way. But dig a little deeper, and something unsettling comes to light. Triangulum appears to be missing one of the universe's most fundamental ingredients, dark matter. This discovery has sent shockwaves through the astronomy community because, according to everything we thought we knew, galaxies shouldn't exist without dark matter. It's the invisible scaffolding that holds them together, the gravitational glue that keeps stars from flying apart. Without it, galaxies like Triangulum simply shouldn't have the mass needed to maintain their shape. Yet here it is, defying expectations. So how did astronomers stumble upon this cosmic anomaly? The key lies in measuring the galaxy's rotation. Stars and gas on the outer edges of a galaxy should move slower if dark matter is present. Its gravity keeps them anchored. But in Triangulum, the outer regions are whipping around far faster than predicted, as if there's nothing holding them back. When researchers crunched the numbers, they realized Triangulum's visible matter alone could account for nearly all its mass, leaving almost no room for dark matter. This flies in the face of decades of galactic models. For years, we've assumed dark matter is the hidden hand shaping every galaxy, from the smallest dwarfs to the largest spirals. Its absence in Triangulum forces us to ask, is this galaxy a rare fluke, or have we been missing something fundamental about how galaxies form? One tantalizing possibility is that Triangulum might have had its dark matter stripped away by a close encounter with Andromeda. Galactic collisions can tear out dark matter, leaving behind a galaxy that looks intact but is missing its invisible backbone. If true, it would mean these cosmic smash-ups are even more transformative than we realized. But there's another, even more radical idea. What if dark matter isn't as universal as we think? Some scientists speculate that certain galaxies might form differently, relying more on ordinary matter than dark matter's pull. If that's the case, Triangulum could be the first clue in rewriting the rulebook on galaxy formation. Of course, not everyone's convinced. Skeptics argue that maybe we're just misreading Triangulum's rotation. Perhaps unusual gas dynamics or hidden stellar streams are throwing off the measurements. Future telescopes, like the upcoming Nancy Grace Roman Space Telescope, might settle the debate by mapping the galaxy's outer reaches in unprecedented detail. For now, Triangulum stands as a cosmic rebel, challenging our assumptions at every turn. Whether it's a galactic oddity or a sign of deeper truths, one thing's clear: the universe still has plenty of surprises up its sleeve. And speaking of surprises, our next stop takes us to two small but fiercely peculiar satellites of Andromeda, each with its own brand of strangeness. Now let's zoom in on two of Andromeda's most intriguing cosmic companions, M32 and M110. These satellite galaxies might be small, but they pack some seriously strange surprises that have astronomers scratching their heads. First up is M32, a tiny elliptical galaxy that punches way above its weight. What makes it so bizarre? It's home to a supermassive black hole that's ridiculously oversized for such a small galaxy. We're talking about a black hole with a mass of around 3 million suns, comparable to the one at the heart of our own Milky Way. But here's the kicker: M32 is hundreds of times smaller than the Milky Way. How does a galaxy this compact end up with such a monstrous black hole? One leading theory suggests M32 was once much larger, perhaps even a grand spiral galaxy like Andromeda, but a brutal encounter stripped away most of its stars. Imagine Andromeda swooping in, ripping apart M32's outer layers, and leaving behind only its dense core and its central black hole. This would explain why the black hole seems so disproportionately massive compared to the galaxy's current size. It's like finding a lion's skull in the skeleton of a house cat, a glaring clue that something dramatic happened in the past. But M32 isn't the only satellite with a shady history. Right beside it floats M110, a dwarf galaxy that looks deceptively peaceful at first glance. Peer a little closer, though, and you'll notice something odd: long, ghostly trails of stars stretching far beyond its main body. These aren't just random scatterings, they're stellar streams, the telltale signs of a violent past. Stellar streams usually form when a galaxy's gravity tears apart a smaller neighbor, scattering its stars into elongated ribbons. The fact that M110 has these streams suggests it might have cannibalized its own satellite galaxies, or perhaps it's still in the process of being shredded by Andromeda's immense gravity. Either way, these starry trails are like cosmic breadcrumbs, leading us back to a history of chaos and collisions. What's fascinating is how different M32 and M110 are despite being neighbors. M32 is dense, compact, and dominated by its overgrown black hole, while M110 is more loosely structured, with stars strewn across space like debris from a wreck. Yet both tell the same overarching story, that even small galaxies are shaped by violent, transformative events. Some astronomers even speculate that M32's black hole might one day merge with Andromeda's central black hole, creating an even more colossal monster. Meanwhile, M110's stellar streams could eventually fade as its stars disperse entirely, leaving behind only whispers of its turbulent past. These two galaxies force us to reconsider what we know about satellite galaxies. They're not just quiet backdrops to Andromeda's grandeur, they're dynamic, evolving, and full of secrets. And if tiny galaxies like these can harbor such extreme features, what other surprises are hiding in the local group's quieter corners? Our next stop takes us back to our own galaxy, where colossal structures known as the Fermi Bubbles stretch high above the Milky Way's core, hinting at an ancient eruption of unimaginable power. Now let's turn our attention to a colossal mystery right in our own cosmic backyard, the Fermi Bubbles. These enormous structures stretch like twin balloons from the heart of the Milky Way, reaching 25,000 light-years above and below the galactic plane. Discovered in 2010 by NASA's Fermi Gamma-Ray Space Telescope, these bubbles are some of the most enigmatic features in our galaxy. At first glance, the Fermi Bubbles might seem like faint, ghostly clouds, but they're anything but ordinary. They're filled with high-energy gamma rays, the most intense form of light in the universe, and they radiate temperatures in the millions of degrees. That kind of energy doesn't just appear out of nowhere. So what created these gargantuan bubbles? One leading theory points to our galaxy's supermassive black hole, Sagittarius, a star. While it's relatively quiet now, astronomers suspect it may have gone through a violent feeding frenzy in the past. Imagine the black hole devouring massive amounts of gas and dust, then belching out colossal jets of energy. These jets could have punched through the Milky Way's disk, inflating the bubbles we see today. It's like a galactic volcano erupting, leaving behind a vast, glowing aftermath. But there's another possibility. The bubbles might be the remnants of an extreme burst of star formation near the galactic center. When massive stars are born in dense clusters, they live fast and die young, exploding as supernovae in rapid succession. These explosions could have blasted gas outward, piling it up into the towering structures we observe. Here's where things get even more interesting. The edges of the Fermi Bubbles aren't smooth, they're jagged, with filaments and substructures that suggest turbulent activity. Some researchers think this means the bubbles are relatively young, perhaps only a few million years old. Others argue that they could be much older, with their complex shapes shaped by magnetic fields or interactions with surrounding gas. What makes the Fermi Bubbles so puzzling is their sheer scale. 25,000 light-years is no small distance. That's roughly a quarter of the Milky Way's diameter. For something that enormous to go unnoticed until 2010 shows just how much we're still learning about our own galaxy. The discovery of the Fermi Bubbles also raises a bigger question. Could similar structures exist in other galaxies? If so, they might be hidden in plain sight, waiting for telescopes sensitive enough to spot them. The more we study these cosmic anomalies, the more we realize that even the familiar Milky Way has its share of spectacular secrets. Up next, we'll take a closer look at the restless heart of our galaxy, Sagittarius, a star itself, and the bizarre flares that make it one of the most unpredictable black holes we know. Now let's zoom in on the dynamic and unpredictable heart of our galaxy, Sagittarius, a star, the supermassive black hole anchoring the Milky Way. While black holes are often imagined as silent, all-consuming voids, Sagittarius, a star, defies expectations with its sporadic and explosive outbursts. Unlike its calmer counterparts in other galaxies, this cosmic heavyweight occasionally wakes from its slumber, unleashing violent flares that light up the surrounding space in X-rays. What makes Sagittarius a star's behavior so unusual? Most supermassive black holes of its size, about 4 million times the mass of our Sun, are relatively quiet, steadily sipping on nearby gas and dust without much fanfare. But Sagittarius, a star, has a temper. Every few years, it erupts with flares so bright they outshine the usual emissions from its accretion disk by hundreds of times. The most dramatic of these occurred in 2022, when astronomers witnessed a record-breaking flare that lasted for several hours, shining 10 times brighter than the black hole's typical output. So what triggers these fiery tantrums? One leading theory suggests that clumps of material orbiting too close to the black hole's event horizon, the point of no return, get stretched and shredded by tidal forces. As these chunks spiral inward, they heat up to extreme temperatures, releasing bursts of X-rays before vanishing forever. Another possibility involves tangled magnetic fields near the black hole's poles snapping and reconnecting, a process that can launch high-energy particles like cosmic fireworks. But here's the real puzzle. Why isn't Sagittarius a star more active? Compared to other supermassive black holes, ours seems oddly underfed. Some researchers think the galactic center simply doesn't have enough gas and dust falling into it to sustain constant flares. Others speculate that past outbursts may have cleared out much of the surrounding material, leaving Sagittarius a star in a sort of cosmic diet. The flares also offer a rare opportunity to study the extreme environment right at the edge of a black hole. By analyzing their light, astronomers have detected strange echoes, delayed signals that suggest some of the energy is bouncing off hidden structures in the vicinity. These could be remnants of ancient stellar collisions or even undiscovered clouds of debris orbiting just outside the danger zone. What's next for unraveling these mysteries? New telescopes like the upcoming Lynx X-ray Observatory aim to capture these flares in unprecedented detail, potentially revealing the precise mechanisms behind their erratic behavior. Every flare we observe is another clue in understanding how supermassive black holes evolve, and why ours seems to play by its own rules. Up ahead, we'll venture beyond the Milky Way to explore another cosmic oddity, the Magellanic Stream, a vast river of gas that links two of our nearest galactic neighbors in a celestial dance. Now let's shift our gaze from the chaotic heart of the Milky Way to a far larger and more mysterious structure drifting just beyond it, the Magellanic Stream. Stretching across an astonishing 150,000 light-years, this colossal ribbon of gas snakes through the local group, connecting two of our most famous galactic neighbors, the Large and Small Magellanic Clouds. But how did this cosmic river form, and why does its existence challenge our understanding of galaxy interactions? For decades, astronomers assumed the Magellanic Stream was a simple tidal tail, a trail of gas ripped from the dwarf galaxies as they orbited the Milky Way. The logic seemed sound. Gravity's pull can stretch and distort smaller galaxies, leaving behind debris like a cosmic breadcrumb trail. But recent simulations have turned this idea on its head. Detailed computer models show that the sheer scale and structure of the stream don't quite match what tidal forces alone should produce. The gas is too evenly distributed, and its velocity is oddly smooth for something supposedly torn apart in a violent gravitational struggle. This inconsistency led researchers to propose a second, far more intriguing culprit: dark matter. The Milky Way isn't just surrounded by visible stars and gas, it's also embedded in a vast halo of this invisible material. As the Magellanic Clouds moved through this halo, their own dark matter might have interacted with it, creating a sort of friction that slowly stripped away their gas over billions of years. Think of it like a boat sailing through water, leaving a wake behind it. In this case, the water is dark matter and the wake is the Magellanic Stream. Some simulations even suggest that the cloud's own dark matter halos were distorted in the process, adding another layer of complexity to the puzzle. But the debate doesn't end there. Observations from the Hubble Space Telescope revealed another twist. Parts of the stream contain far more heavy elements like oxygen and silicon than expected. If the gas came purely from the Magellanic Cloud's outer regions where stars are scarce, it should be relatively pristine. Instead, these heavier elements hint that supernova explosions within the clouds may have ejected enriched material into the stream long before tidal forces or dark matter took effect. It's a cosmic recycling project on an epic scale, with dying stars contributing to the very structure we see today. The mystery deepens when we consider the stream's future. Current measurements show it's gradually falling toward the Milky Way, and in a few 100 million years, it could fuel a new wave of star formation in our galaxy. Yet, even as we piece together its origins, questions remain. Why does the stream curve the way it does? Why do some sections appear denser than others? And could similar structures exist around other galaxies hidden from our view? Up next, we'll dive into one of the most vibrant regions within the stream's parent galaxies, the Large Magellanic Cloud superbubble N51, a celestial powerhouse where stars are born and die in spectacular fashion. Moving deeper into the cosmic tapestry, we arrive at one of the most dynamic nurseries of star birth and destruction in our galactic neighborhood, the Large Magellanic Cloud superbubble N51. This colossal cavity, stretching an incredible 300 light-years across, is a testament to the raw power of stars shaping their own surroundings. Imagine a bubble blown by a child, but instead of soap and air, this one is sculpted by the relentless winds of massive stars and the violent deaths of supernova. At the heart of N51 lies a cluster of young, fiery stars, each many times more massive than our Sun. These stellar giants don't just sit quietly, they blast out torrents of charged particles and radiation, carving cavities into the surrounding gas. Over time, these winds collide with slower-moving material, creating shockwaves that ripple through space. Chandra X-ray Observatory's sharp vision reveals these shockwaves as brilliant filaments, glowing with energy as they heat the gas to millions of degrees. But the drama doesn't stop there. When the most massive stars in the cluster reach the end of their lives, they explode as supernova, unleashing enough energy to further inflate the bubble and trigger new rounds of star formation at its edges. What makes N51 truly special isn't just its size or the violence within it, it's the way it showcases the life cycle of stars in action. The dense gas along the bubble's edges, compressed by shockwaves, becomes the birthplace of new stars. In some regions, Hubble's keen eye has spotted infant stars still wrapped in their dusty cocoons, emerging from the chaos like cosmic phoenixes. It's a self-perpetuating cycle. Stars are born, they shape their environment, they die explosively, and in doing so, they create the conditions for the next generation. But N51 isn't alone in this process. Similar superbubbles have been spotted in other galaxies, yet this one stands out for its accessibility. Because the Large Magellanic Cloud is so close, just 160,000 light-years away, we can study it in extraordinary detail. The data collected here helps astronomers understand how these structures influence galactic ecosystems on larger scales. Without them, galaxies might lack the turbulent environments needed to recycle gas and spark new star formation, leaving them stagnant and lifeless, yet mysteries remain. Why does N51 have such a sharp, well-defined boundary in some areas but appear frayed in others? Could magnetic fields play a role in shaping its structure? And how do the smaller bubbles within it interact with the larger one? Each answer only leads to more questions, reminding us that even the most violent cosmic phenomena are part of a delicate balance. Next, we'll venture to another corner of the local group, where an entire galaxy defies expectations by stretching not just across the sky, but into the depths of space itself. The Small Magellanic Cloud's unexpected three-dimensional shape. Now let's shift our gaze to another cosmic oddity in our galactic backyard, the Small Magellanic Cloud. At first glance, this dwarf galaxy seems like a typical, wispy patch of light, but here's the twist: it's not flat like most galaxies. Instead, it stretches deep into space toward and away from us, giving it a surprising three-dimensional structure. Imagine holding a piece of paper. That's how we usually picture galaxies, thin and flat. But the small Magellanic Cloud, it's more like a crumpled ball of paper with stars scattered in all directions. This unusual shape wasn't obvious at first. For decades, astronomers assumed it was a flat disk, much like its larger neighbor, the Large Magellanic Cloud. But microlensing surveys, a clever technique that tracks how light bends around unseen objects, revealed the truth. As stars in the small Magellanic Cloud pass in front of more distant background stars, their gravity slightly magnifies and distorts the light. By measuring these subtle changes, scientists pieced together the galaxy's depth, discovering it extends tens of thousands of light-years along our line of sight. So why does this galaxy defy the flat disk norm? The answer lies in its turbulent past. The small Magellanic Cloud hasn't had an easy life. Gravitational tugs from the Milky Way and the Large Magellanic Cloud have stretched and twisted it over billions of years. Some simulations suggest it might even have collided with its larger neighbor in the distant past, scattering stars into this chaotic, three-dimensional arrangement. Unlike orderly spiral galaxies where stars rotate in a neat plane, this dwarf galaxy's stars move in all directions like bees buzzing around a hive. Yet the surprises don't end there. The small Magellanic Cloud's depth isn't uniform. Some regions are more stretched out than others. Astronomers have identified at least two distinct stellar populations, one closer to us and another much farther away. This could be evidence of multiple merger events where smaller galaxies were swallowed up, leaving their stars in different orbits. Alternatively, the Milky Way's gravity might be peeling away layers of the galaxy, creating this lopsided structure. Whatever the cause, it's clear this little galaxy has endured a dramatic history. What's fascinating is how this discovery reshapes our understanding of dwarf galaxies. For years, they were considered simple, primitive systems, leftovers from the early universe. But the small Magellanic Cloud's complex structure suggests they're dynamic places, sculpted by interactions and full of hidden depths, quite literally. It also raises new questions. Are other dwarf galaxies similarly puffed up, or is this one special? Could its three-dimensional shape explain why it's forming stars at a different rate than its flatter counterparts? As we pull back from this celestial oddity, remember, sometimes the universe's most intriguing secrets aren't about vast scale or explosive power, but the subtle ways things aren't quite what they seem. Next, we'll turn to another dwarf galaxy that's equally puzzling, but for a very different reason: Leo 1 and its unexpectedly massive dark matter halo. Now let's turn our attention to something that defies expectations: the dwarf galaxy Leo 1. At first glance, it seems unremarkable, just a faint smudge of stars orbiting the Milky Way. But here's the cosmic curveball. Despite its small size, Leo 1 is hiding a dark matter halo so massive it rivals our own galaxies. That's like finding a tiny pebble with the weight of a boulder. So how did astronomers stumble upon this oddity? It all comes down to the way stars move within Leo 1. Normally, in a small galaxy, stars drift at relatively slow speeds held by a modest gravitational pull. But when researchers measured the velocities of Leo 1 stars, they were stunned. These stars were zipping around far faster than the visible mass of the galaxy could explain. The only possible culprit: a colossal amount of unseen dark matter, so much that it rivals the Milky Way's own halo. For context, the Milky Way is about 20 times wider and contains thousands of times more stars. Yet somehow, this little satellite has a dark matter halo that's nearly as hefty. What makes this even stranger is Leo 1 location. It's one of the most distant satellites of the Milky Way, orbiting nearly 800,000 light-years away. That's so far out that the Milky Way's gravity should barely influence it. Yet instead of being a loose, dispersed collection of stars, as we'd expect for a galaxy on the fringe, Leo 1 holds itself together tightly, almost defiantly. If it weren't for that invisible dark matter anchor, its stars would have scattered into the void long ago. This discovery has led to two compelling theories. First, Leo 1 might be a failed galaxy, a cosmic underachiever that started with the same raw materials as giants like the Milky Way, but never quite got its act together. Early in the universe, vast clouds of gas and dark matter clumped together, and while most grew into majestic spirals, a few might have stalled, leaving behind these odd, dark matter-rich dwarfs. The second theory is even more dramatic. Leo 1 could be the remnant of a violent merger. Imagine two small galaxies smashing together long ago. The collision would have stripped away most of their stars and gas, leaving behind a dense core of dark matter, essentially a galactic ghost haunting the outskirts of the Milky Way. But here's where things get really interesting. Leo 1 dark matter isn't just abundant, it's also distributed unusually. Most galaxies have dark matter concentrated at their centers, but Leo 1 seems more spread out, almost like a faint, giant cloud enveloping the stars. This has forced astronomers to rethink how dark matter behaves in small galaxies. Could there be different flavors of dark matter, or does it interact in ways we haven't accounted for in our models? What's wild is that Leo 1 isn't alone. A handful of other ultra-faint dwarfs like Draco and Ursa Minor also show signs of disproportionate dark matter. But Leo 1 stands out because of its extreme distance and the sheer scale of its halo. It's making scientists question whether these tiny galaxies are actually the most dark matter-dominated objects in the universe, far more so than the biggest spirals. That flips our entire understanding of galaxy formation on its head. As we wrap up this segment, remember, sometimes the universe's most profound mysteries come in the smallest packages. Up next, we'll explore another dwarf galaxy that breaks the rules, the Fornax dwarf, where globular clusters abound in ways no one predicted. Now let's shift our gaze to another cosmic oddball, the Fornax dwarf. At first glance, this faint dwarf galaxy might seem like just another speck in the Milky Way's entourage, but here's what makes it extraordinary. It's packed with not one, not two, but 6 globular clusters. That's a staggering number for a galaxy so small, and it's left astronomers scratching their heads for decades. To put this into perspective, let's talk about globular clusters. These are dense, spherical collections of ancient stars, often numbering in the hundreds of thousands. They're like cosmic beehives buzzing with stellar activity. Most large galaxies, including our Milky Way, host a respectable number of them, around 150 in our case. But for a dwarf galaxy like Fornax, which is thousands of times smaller and less massive, even a single globular cluster would be noteworthy. 6, that's downright bizarre. So how did Fornax end up with such a rich collection? The leading theory points to a turbulent past. Dwarf galaxies orbiting the Milky Way often have rough encounters, gravitational tugs, and collisions that strip away their stars and gas. Yet Fornax has somehow held onto its clusters despite these challenges. One possibility is that it arrived in the Milky Way's orbit relatively recently, meaning it hasn't suffered as much disruption as other dwarfs. But even that doesn't fully explain the overabundance. Another angle involves the clusters themselves. Unlike the Milky Way's globulars, which are ancient relics from the early universe, some of Fornax's clusters appear younger. This suggests they might have formed during or after the galaxy's interactions with the Milky Way. Imagine a cosmic game of pinball where gravitational encounters compress gas and trigger new star formation, leading to fresh clusters. It's as if Fornax defied the odds, not only keeping its old clusters but also forging new ones along the way. But here's where the mystery deepens. Some of Fornax's globulars are unusually large, so big that they blur the line between a cluster and a tiny dwarf galaxy. One in particular, known as Fornax 4, is so massive that it might actually be the stripped core of an even smaller galaxy that Fornax absorbed long ago. If true, this would mean Fornax didn't just form its clusters, it stole some of them. That would make it a cosmic kleptomaniac hoarding stellar treasures from its neighbors. Adding to the intrigue, Fornax's clusters aren't all clustered together. They're scattered across the galaxy, some even lingering in its outer halo. This distribution suggests that Fornax's gravitational grip is surprisingly strong for its size, another hint that dark matter might play a role. Just like Leo 1, Fornax could be hiding far more unseen mass than its visible stars reveal, helping it retain its globulars despite the Milky Way's gravitational pulling. What's truly fascinating is how Fornax compares to other dwarfs. Most of the Milky Way's satellite galaxies have lost their globular clusters entirely, their treasures ripped away by tidal forces. Yet Fornax holds onto its 6 almost defiantly. This makes it a cosmic outlier, challenging our assumptions about how dwarf galaxies evolve. As we peel back the layers of this mystery, one thing becomes clear. Fornax isn't just a passive spectator in the Milky Way's orbit. It's a survivor clinging to its stellar jewels against all odds. And that raises an even bigger question. What other secrets are these tiny galaxies hiding? Up next, we'll dive into the Draco dwarf, where dark matter doesn't just lurk, it absolutely dominates. Now let's journey deeper into the local group's dark side, literally. Meet the Draco dwarf, a galaxy so dominated by dark matter that it bends the rules of cosmic physics. While most galaxies have a mix of stars, gas, and dark matter, Draco is in a league of its own. A staggering 99% of its mass is invisible dark matter, with just a sprinkling of visible stars. This makes it one of the most extreme examples of dark matter's grip on the universe, and its stars are telling a bizarre story. Picture this. Stars inside a galaxy typically move at speeds dictated by the visible matter, stars and gas that creates gravity. But in Draco, the stars are racing around like they're being pulled by something far more massive than what we can see. Their velocities are so high that if the galaxy were made only of the stars we observe, they should have flung themselves into space long ago. The fact that they're still tightly bound means an enormous, unseen force is holding them together. That force, a dense halo of dark matter, invisible but undeniably powerful. What's even more puzzling is how Draco compares to other dwarf galaxies. Take the Carina dwarf, another satellite of the Milky Way. Carina has a more normal distribution of dark matter, still significant, but nowhere near Draco's extreme ratio. Carina's stars move at slower, more predictable speeds, aligning with the amount of visible mass. This stark difference raises a critical question. Why is Draco so overloaded with dark matter while others, like Carina, aren't? One theory suggests Draco might be a primordial relic, a surviving fragment from the early universe that avoided major collisions or stripping events. Over billions of years, most dwarf galaxies had their dark matter diluted or stripped away by interactions with larger galaxies. But Draco, perhaps due to its orbit or sheer luck, held onto its original dark matter halo almost untouched. Another idea proposes that Draco's dark matter is clumpier than usual, concentrating in ways that amplify its gravitational influence on stars. Then there's the role of tidal forces. The Milky Way's gravity can stretch and distort satellite galaxies, often pulling away their stars and gas. But Draco's stars remain tightly bound, another clue that its dark matter is acting like an invisible shield, protecting it from complete disruption. This resilience makes Draco a key target for scientists studying dark matter's nature, especially since its extreme composition could hint at how dark matter behaves on smaller scales. But here's where the plot thickens. Some astronomers argue Draco's dark matter dominance isn't unique. It's just the most obvious case. Many ultra-faint dwarfs might be similarly dark matter-rich, but their stars are so sparse and dim that we can't measure their motions as easily. Draco, with its slightly brighter stellar population, gives us a rare window into this shadowy realm. Yet mysteries remain. If dark matter is so abundant in Draco, why hasn't it collapsed into a denser core as some models predict? Observations show its dark matter is spread relatively smoothly, contradicting certain theories about how dark matter should behave. This mismatch has led to alternative ideas like self-interacting dark matter particles that collide and scatter, preventing them from clumping too tightly. The Draco dwarf forces us to rethink the textbook image of galaxies. It's not just a collection of stars, it's a ghostly scaffold of dark matter with stars as mere ornaments. By studying its extremes, we edge closer to unlocking dark matter's secrets, one of the greatest puzzles in modern astronomy. Next up, we'll explore the Sculptor Galaxy, where asymmetry tells a tale of cosmic violence and disruption. Now let's turn our attention to the Sculptor Galaxy, where asymmetry tells a story of cosmic chaos. Unlike the smooth, symmetrical halos we expect from most galaxies, Sculptor's outer regions are lopsided, a clue that something dramatic happened in its past. Imagine a perfectly round balloon pinched on one side, warping its shape. That's the Sculptor Galaxy, but on a galactic scale, with its stars stretched and twisted into an uneven, almost distorted halo. This irregularity isn't just a visual oddity, it's evidence of a violent history. The leading theory, a past collision with another galaxy. When two galaxies interact, their gravitational forces can pull and distort each other, leaving behind scars in the form of lopsided star distributions. The Dark Energy Survey, a massive mapping project of the cosmos, has captured Sculptor's distorted halo in stunning detail. These maps reveal streams and clumps of stars extending far beyond the galaxy's main disk, like splatters of paint flung from a brush. These aren't random, they're the aftermath of a gravitational tug of war, remnants of a smaller galaxy torn apart and absorbed by Sculptor. But collisions aren't the only possibility. Another explanation points to dark matter. If Sculptor's dark matter halo, the invisible scaffold surrounding it, is itself uneven, that could warp the distribution of stars, pulling them more to one side. Astronomers are still debating which force played the bigger role, but one thing is clear: Sculptor's asymmetry challenges our assumptions about how galaxies evolve. Most models predict smooth, balanced halos, yet here we see a galaxy that defies that expectation. What makes Sculptor especially intriguing is its relative isolation. Unlike galaxies in dense clusters which frequently collide, Sculptor sits in a quieter part of space. So if it did suffer a past merger, the event must have been rare, or the intruder galaxy was exceptionally unlucky. Alternatively, the lopsidedness could be ancient, a relic from Sculptor's formation billions of years ago when the universe was far more chaotic. Then there's the question of timing. If a collision did happen, was it a single catastrophic event or a series of smaller encounters over time? The Dark Energy Survey's maps show multiple layers of distortion, hinting at a complex history. Some of the outermost stars are so loosely bound they're practically escaping, suggesting the galaxy might still be settling after the disruption. Sculptor's asymmetry isn't just a curiosity, it's a window into galactic survival. Most galaxies, including our Milky Way, show signs of past mergers, but Sculptor's lopsided halo offers a snapshot of how these events play out over cosmic timescales. By studying its shape, astronomers can reconstruct the forces that shaped it, testing theories about galaxy growth and dark matter's role. Up next, we'll shift focus to something equally mysterious: the NGC 6822's blue blobs, isolated pockets of young stars where they shouldn't exist. How did these stellar nurseries form without the usual gas clouds? Stay tuned. Moving beyond the Sculptor Galaxy's twisted halo, let's venture into another cosmic head-scratcher: the peculiar blue blobs of NGC 6822. This irregular galaxy, nicknamed Barnard's Galaxy, hosts something that shouldn't exist: vibrant young star clusters blazing in the middle of nowhere, far from the gas clouds that typically birth stars. Picture stumbling upon a bustling playground in a desert, no parents, no supplies, just kids playing. That's the level of mystery these blue blobs present. Hubble Space Telescope first spotted these isolated stellar nurseries, and they immediately defied expectations. Normally, stars form in dense clouds of gas and dust, where gravity pulls material together until it ignites nuclear fusion. But these clusters are orphans, floating in empty space with no visible fuel source around them. How did they get there? One theory suggests they were born in hidden gas pockets too faint for telescopes to detect. Imagine gas so diffuse it's like a wisp of smoke, just enough to form stars but nearly invisible to us. If true, it would mean our current tools are missing a crucial piece of the star formation puzzle. Another idea is even more dramatic. These blobs might be remnants of a galactic collision. When galaxies interact, tidal forces can rip gas streams loose, flinging them far from their origins. Over time, these isolated gas clumps could collapse into stars, leaving behind blue blobs like cosmic breadcrumbs. Supporting this, NGC 6822 shows faint tidal tails, filaments of stars and gas stretched by gravitational encounters. But here's the twist: the galaxy appears relatively undisturbed, with no obvious partner nearby. So if a collision happened, it was either ancient or with something incredibly faint, like a dark matter-dominated dwarf. Then there's the rogue star cluster hypothesis. Some propose these blobs didn't form in place but were ejected from denser regions of NGC 6822 by gravitational slingshots. Supernova explosions or interactions with massive objects could have kicked them outward like pebbles shot from a sling. Hubble's sharp eyes reveal some blobs are moving unusually fast, lending credence to this idea. But ejection alone doesn't explain why they're so blue, a sign of youth. If they were ancient wanderers, they'd likely appear redder from aging stars. The most puzzling blobs are those with multiple generations of stars. Normally, a cluster forms all its stars around the same time. Yet some blue blobs contain both young, blue stars and older, redder ones, suggesting they've somehow sustained star formation over time without a clear gas supply. One explanation: they're hoarding fuel. Small clusters might retain enough gas from their birth to form new stars intermittently, like a campfire fed by hidden embers. Alternatively, they could be cannibalizing smaller gas clouds drifting too close, though none have been detected yet. What makes NGC 6822's blue blobs invaluable is their defiance of textbook star formation. They force astronomers to reconsider how versatile the universe can be. Maybe gas doesn't always need to be dense to collapse. Perhaps turbulence or magnetic fields help sparse gas clump together. Or maybe our understanding of galactic collisions is incomplete, and even quiet galaxies like this one harbor violent pasts. As Hubble and newer telescopes like Webb study these blobs, they're uncovering more questions than answers. Each discovery peels back another layer, showing how much we still don't know about the cosmos. Up next, we'll explore another rebel, Ike-10, a galaxy teeming with stellar mass black holes where the rules of cosmic demography seem rewritten. How did this tiny galaxy end up with so many black holes? That's a story of chaos and cosmic excess. Now, shifting our gaze from the enigmatic blue blobs, we land on IC-10, a small but wildly explosive galaxy. What makes this one stand out isn't just its frenetic star formation, but its shocking abundance of stellar mass black holes. Imagine a quiet neighborhood where every few houses hides a hidden vault. IC-10 is like that, but with black holes lurking in its stellar fabric. This starburst galaxy, located in Cassiopeia, is a cosmic powerhouse, churning out new stars at a rate that puts most galaxies to shame. But here's the twist: with all those massive stars being born, many are dying in dramatic fashion, collapsing into black holes. What's bizarre is how many of these black holes are paired with stars, creating what astronomers call X-ray binaries. These duos are like cosmic dance partners, where the black hole steals material from its companion star, heating it to millions of degrees and releasing intense X-rays. Normally, you'd expect a handful of these systems in a galaxy IC10 size, but IC10, it's overflowing with them. Why the surplus? Blame the Wolf-Rayet stars. These are rare, massive stars that shed their outer layers at dizzying speeds, exposing their scorching cores. They're the divas of the stellar world, short-lived, extravagant, and destined to explode. In IC10, Wolf-Rayet stars are everywhere, a sign of its breakneck star formation. When these stars eventually go supernova, they often leave behind black holes. And because IC10 is so densely packed, these black holes have a high chance of pairing up with other stars, creating those X-ray binaries we've detected. But there's another layer to this mystery. IC10's black holes aren't just numerous, they're also unusually active. Some are devouring their companion stars at rates that defy expectations. One leading theory suggests that the galaxy's low metallicity, meaning it lacks heavier elements, plays a role. Stars born in metal-poor environments tend to retain more mass as they age, leading to heftier black holes when they collapse. These bigger black holes have stronger gravity, pulling in material more aggressively and shining brighter in X-rays. What's even more intriguing is how IC10's black hole boom might be temporary. Starburst galaxies like this one burn through their gas reserves quickly, and once the star-forming frenzy ends, so too might the black hole production line. That makes IC10 a fleeting laboratory for studying how extreme environments shape black hole populations. Telescopes like Chandra have been instrumental in mapping these X-ray binaries, revealing patterns that challenge our models of black hole formation. IC10 forces us to rethink the rules. Most galaxies have a quiet equilibrium between star birth and death, but here everything's turned up to 11. It's a reminder that the universe loves outliers, places where the usual playbook doesn't apply. Up next, we'll encounter a galaxy that did the opposite of IC10, the Pegasus dwarf, where star formation abruptly stopped billions of years ago. What silenced this galaxy, and what can its frozen history teach us? Stay tuned. Now, let's turn our attention to a galaxy that's the polar opposite of IC10, where the cosmic fireworks fizzled out long ago. Meet the Pegasus dwarf, a small, unassuming galaxy with a puzzling secret. Its stars stopped forming abruptly 8 billion years ago, freezing it in time while the rest of the universe carried on. This tiny galaxy, a satellite of our Milky Way, is what astronomers call quenched. Unlike active galaxies where new stars are born, the Pegasus dwarf's stellar production shut down mysteriously early in cosmic history. The question is, why? Two leading theories compete for answers. The first points to tidal stripping, the idea that our Milky Way's gravity yanked away the Pegasus dwarf's gas, the raw material for making stars. Without gas, star formation grinds to a halt. The second theory blames cosmic reionization, a period when the universe's first stars and galaxies flooded space with intense ultraviolet light, heating and dispersing gas in small galaxies like Pegasus, effectively starving them. Evidence for tidal stripping comes from the galaxy's current state. The Pegasus dwarf has almost no gas left today, and its remaining stars are old, with few signs of younger generations. If the Milky Way's gravity was the culprit, we'd expect to see stretched out trails of stars or gas, telltale signs of a galaxy being pulled apart. But so far, these tidal tails haven't been spotted definitively. That leaves room for reionization as the alternative. During this era, roughly 13 billion years ago, the universe transitioned from darkness to light, and small, fragile galaxies like Pegasus might have had their gas blown away by the sudden flood of energy. Here's where it gets even more intriguing. The Pegasus dwarf isn't alone. Other tiny galaxies in the local group show similar quenching, but the timing differs. Some shut down early, like Pegasus, while others kept forming stars much longer. This suggests that both tidal stripping and reionization could be at play, depending on a galaxy's environment and mass. Pegasus, being particularly lightweight, might have been a sitting duck for reionization's effects, while larger dwarfs could resist longer until Milky Way's gravity caught up with them. What makes the Pegasus dwarf so valuable is its role as a cosmic time capsule. Its ancient stars offer a snapshot of the early universe, untouched by later star-forming chaos. By studying their composition, astronomers can piece together conditions from billions of years ago. For instance, the lack of heavy elements in Pegasus's stars hints that it never had the chance to enrich itself with metals forged in later supernova, another clue that its star formation ended prematurely. The mystery of its quenching isn't just about Pegasus, it's about understanding how small galaxies evolve. Were they victims of their environment, or did internal processes doom them? Up next, we'll explore a galaxy that avoided these pitfalls entirely. The WLM Galaxy, a pristine relic that somehow dodged cosmic pollution and kept its ancient chemistry intact. How did it stay so untouched, and what can it teach us about the early universe? The answers might surprise you. Now, shifting our gaze to a cosmic relic that defies the usual fate of galaxies, we encounter the WLM Galaxy, a tiny, isolated island universe that has somehow kept its chemistry astonishingly pure. While most galaxies in the local group have been chemically altered by eons of star formation and collisions, WLM remains a time capsule from the early universe, its composition nearly unchanged for billions of years. What makes WLM so special is its incredibly low metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium. In WLM, these heavy elements are incredibly scarce, making it a close match to the pristine galaxies that formed just after the Big Bang. Unlike the Milky Way or Andromeda, where generations of stars have enriched the gas with metals through supernova and stellar winds, WLM's isolation has kept it chemically untouched. Nestled about 3 million light-years away from the Milky Way, far from the crowded center of the local group, it has avoided the gravitational tug of war and gas exchanges that pollute most galaxies over time. This isolation is key to its purity. Most galaxies in dense environments like our own constantly interact with neighbors, swapping gas, merging, or being stripped by larger galaxies. These interactions trigger star formation, which in turn produces heavier elements, but WLM, floating alone in the cosmic boondocks, has had no such disruptions. Its star formation has been slow and steady, with long quiet periods where nothing disturbs its gas. The result, a galaxy that's essentially a living fossil, offering us a direct glimpse into the conditions of the early universe. Studying WLM stars tells a fascinating story. The youngest stars here still have metal levels hundreds of times lower than the Sun's. Even more striking, the ratio of certain elements like oxygen to iron matches predictions for the universe's first galaxies. This suggests WLM's chemistry hasn't been diluted by later generations of stars or external contamination. For astronomers, it's like finding an untouched sample of the primordial cosmos, letting them test theories about how the first stars and galaxies formed. But how did WLM manage to stay so clean? One clue lies in its small size and shallow gravity well. Unlike bigger galaxies, it lacks the pull to hold onto gas ejected by supernova. Instead, these explosions blow material straight out into intergalactic space, preventing it from being recycled into new stars. This self-cleaning mechanism ensures that each generation of stars forms from nearly pristine gas, keeping WLM's metallicity shockingly low. The implications are profound. WLM challenges the assumption that all galaxies grow dirtier over time. Its existence proves that some corners of the universe can remain chemically pristine even after billions of years. By comparing it to metal-rich galaxies, astronomers can unravel how environment shapes a galaxy's evolution and why some, like WLM, resist the cosmic trend toward pollution. Up next, we'll examine a galaxy that couldn't be more different, the Aquarius dwarf, whose stars have been stretched into ethereal streams by the Milky Way's gravity. How did this dramatic transformation happen, and what can these tidal tales teach us about the hidden forces shaping our galactic neighborhood? The answers reveal the violent beauty of cosmic collisions. Now, as we turn our attention to a dramatic cosmic tug-of-war, we find the Aquarius dwarf, a galaxy caught in the gravitational grasp of the Milky Way, its stars pulled into breathtaking tidal tales that stretch across the sky. Unlike the untouched purity of the WLM galaxy, the Aquarius dwarf tells a story of violent transformation, its structure reshaped by the relentless pull of our own galaxy. The Aquarius dwarf wasn't always this fragmented. Once it was a typical small galaxy held together by its own gravity. But as it ventured too close to the Milky Way, our galaxy's far stronger gravity began to stretch it apart. Imagine grabbing a handful of glitter and slowly pulling it into long, shimmering streaks. That's essentially what's happening here, but on a galactic scale. Over billions of years, the Milky Way's tidal forces have ripped stars away from the Aquarius dwarf, leaving behind luminous trails that snake through space. These tidal tales aren't just beautiful, they're packed with clues about the Milky Way's past and the nature of dark matter. The way the stars are distributed in these streams helps astronomers map the Milky Way's gravitational field with incredible precision. Because gravity is the only force shaping these trails, their structure reveals the hidden mass of our galaxy, including the elusive dark matter halo that surrounds us. One of the most fascinating discoveries linked to the Aquarius dwarf is the field of streams, a vast network of stellar rivers crisscrossing the Milky Way's outskirts. This field, first mapped in detail by the Sloan Digital Sky Survey, is like a cosmic crime scene, showing the remnants of multiple small galaxies torn apart by our galaxy's gravity. The Aquarius dwarf's tidal tales are just one thread in this intricate web, evidence of a long history of galactic cannibalism. Simulations of the Aquarius dwarf's destruction have given astronomers a front-row seat to its final act. By modeling the Milky Way's gravity and the dwarf galaxy's trajectory, researchers can rewind time, watching as the streams of stars gradually reassemble into the original dwarf. These simulations don't just reconstruct the past, they help predict the future, showing how other satellite galaxies might one day meet the same fate. What makes the Aquarius dwarf particularly intriguing is the asymmetry of its tidal tails. Unlike some disrupted galaxies where debris spreads evenly, this dwarf's stars stretch out more on one side. This unevenness suggests the Milky Way's dark matter halo isn't perfectly smooth. It might have lumps or irregularities that tug harder in certain directions, leaving this unique fingerprint on the Aquarius dwarf's remains. The study of these tidal streams isn't just about destruction, it's also about survival. Some stars stripped from the Aquarius dwarf are still bound together in dense clumps, resisting total disintegration. These surviving knots hint at how much dark matter might have been inside the original dwarf, acting like cosmic glue to hold these groups together even as the rest of the galaxy was shredded. As we piece together the story of the Aquarius dwarf, we're reminded that our galaxy isn't just a static island of stars. It's a dynamic predator growing by consuming smaller neighbors. Every stellar stream is a fossil of these ancient encounters, a testament to the Milky Way's violent history. Next, we'll explore another lonely outpost of the local group, the Tucana dwarf, a solitary galaxy that has somehow avoided the fate of the Aquarius dwarf. What secrets does its isolation hold, and why has it remained untouched while others were pulled apart? The answers might rewrite our understanding of galactic survival. Leaving behind the chaos of galactic collisions, we now encounter a true cosmic hermit, the Tucana dwarf. Unlike the Aquarius dwarf, which was torn apart by the Milky Way's gravity, This small galaxy has somehow avoided all major interactions, drifting alone in the outskirts of the local group for billions of years. Its isolation isn't just unusual, it's a puzzle that challenges our understanding of how galaxies evolve. Most dwarf galaxies in the local group cluster near giants like the Milky Way or Andromeda, caught in their gravitational pull. But Tucana defies expectations. Located over 1 million light-years from the nearest large galaxy, it floats in near-total solitude. Even more puzzling, its stars show no signs of past collisions or distortions, no tidal tails, no warped disk, no missing dark matter. It's as if the Tucana dwarf has existed in a protective bubble, untouched by the violent mergers shaping its neighbors. One explanation for its loneliness could be its orbit. Unlike most satellites, Tucana isn't circling a larger galaxy. It moves in an unusually wide path around the local group's outskirts, avoiding close encounters. Think of it like a comet with an extremely long orbit, only swinging through the inner solar system very rarely. Tucana's trajectory might have kept it far enough away to escape major disturbances. But that still doesn't fully explain why it never wandered too close to another galaxy, especially over billions of years of cosmic history. Another clue lies in Tucana's unusual chemistry. Studies reveal its stars have surprisingly low metallicity, meaning they contain few elements heavier than hydrogen and helium. This suggests Tucana formed most of its stars very early in the universe's history, when heavier elements were scarce and then somehow stopped forming new ones. Without later waves of star birth, it never developed the dense gas clouds that often trigger interactions between galaxies. It's like a fossil from the early cosmos, preserved in near-original condition. The mystery deepens when we compare Tucana to its so-called twin, the Pegasus dwarf. Both galaxies share similar sizes and shapes, yet Pegasus shows clear signs of past interactions, tidal distortions, and disrupted star clusters. So why did one remain pristine while the other didn't? Some astronomers speculate Tucana might have originated in an emptier region of space where fewer galaxies roamed nearby, leaving nothing to collide with. Others propose that dark matter might play a role. Perhaps Tucana's dark matter halo is just dense enough to shield it from gravitational disruptions. The biggest question, though, is what Tucana's isolation tells us about galaxy survival. Most small galaxies eventually get absorbed by larger ones, but Tucana proves exceptions exist. Could there be other, lone wolf galaxies hiding in the local group's fringes, unnoticed because they're too faint? Future telescopes like the Vera Rubin Observatory might uncover more of these reclusive systems, rewriting our maps of the cosmic neighborhood. For now, the Tucana dwarf stands as a quiet rebel, a galaxy that refused to follow the usual rules of cosmic evolution. Its untouched stars are like time capsules, offering a rare glimpse into the universe's early conditions. Next, we'll shift focus to another enigma, Andromeda 19. A galaxy so faint and sparse it's been called the ghost of the local group. How does something so barely there hold itself together? The answer might redefine what we thought galaxies could be. Stepping into the realm of cosmic ghosts, we arrive at Andromeda 19, a galaxy so faint and spread out it defies everything we thought we knew about how galaxies hold themselves together. Imagine a city where the buildings are scattered miles apart, with just a few streetlights flickering in the vast darkness. That's Andromeda 19, a place where stars are so few and far between, they barely seem to belong to the same structure at all. This galaxy is a textbook example of what astronomers call an ultra-diffuse galaxy. Its stars are stretched across an area as wide as the Milky Way, but with only 1% of our galaxy's star count. If you stood on a planet in Andromeda 19, the night sky would be nearly black, with just a handful of distant suns visible to the naked eye, the strangest part. Despite its wispy appearance, this galaxy isn't being torn apart. It's holding together somehow, even though its stars are so sparse that gravity seems barely strong enough to keep them linked. To understand how this is possible, scientists have turned to dark matter. Most galaxies, including our own, are anchored by enormous halos of this invisible substance whose gravity keeps stars in orbit. But Andromeda 19's dark matter halo appears oddly unbalanced. Some models suggest it might be stretched into an elongated shape, like a cosmic taffy pull, with gravity just strong enough at the core to prevent total disintegration. Others propose that its dark matter is distributed in a unique, clumpy pattern, creating fragile pockets of stability. The real shocker, though, is how it compares to other ultra-diffuse galaxies. Take Dragonfly 44, a similar ghostly galaxy in the Coma cluster. Dragonfly 44 is roughly the same size as the Milky Way, but emits only 1% of the light. Yet, unlike Andromeda 19, it's packed with dark matter so much that its mass rivals the Milky Way's, despite having almost no visible stars. This raises a baffling question. Why do some ultra-diffuse galaxies like Dragonfly 44 have monstrous amounts of dark matter while others, like Andromeda 19, seem to barely cling to theirs? One leading theory is that Andromeda 19 might be a failed galaxy. Early in the universe's history, it could have started forming stars but ran out of gas, literally. Without enough fuel to create new stars, it became a skeletal relic. Alternatively, it might be the remnant of a larger galaxy that was ripped apart by tidal forces, leaving behind only the most loosely bound stars. The fact that it orbits Andromeda supports this idea, as our neighboring galaxy's gravity could have stripped away its outer layers over billions of years. But here's where things get even weirder. Recent observations suggest Andromeda 19 isn't alone. Dozens of these ultra-diffuse galaxies have been spotted in the local group, and many more likely lurk undetected because they're so faint. Some might even be dark galaxies, structures made almost entirely of dark matter, with just a sprinkling of stars. If true, this would mean our cosmic neighborhood is teeming with invisible giants, silently drifting alongside the galaxies we can see. What does this mean for our understanding of galaxies? For one, it challenges the assumption that a galaxy needs a dense core of stars to survive. Andromeda 19 proves that galaxies can exist in states so tenuous they're barely there at all. It also hints that dark matter, already mysterious, might behave in ways we haven't yet accounted for, clustering differently in some galaxies than in others. The discovery of galaxies like this forces astronomers to rethink the rules. Maybe the universe isn't just building grand spirals and glowing ellipticals. Maybe it's also creating fragile, ghostly whispers of galaxies, so faint we've only just begun to notice them. As telescopes grow more sensitive, we'll likely find more of these ethereal structures, each with its own story to tell. Now, let's turn our attention to another cosmic oddity, Triangulum 2, a tiny galaxy where the faint glow of gamma rays might be the signature of something even more elusive, dark matter annihilating itself in the depths of space. Could this finally be the clue that unravels one of the universe's greatest mysteries? The answer lies ahead. Now, let's zoom in on a cosmic puzzle hiding in plain sight, Triangulum 2. This tiny, unassuming galaxy, barely a speck next to giants like Andromeda, might hold the key to one of astronomy's biggest mysteries, dark matter. But here's the twist: what some scientists think is evidence of dark matter annihilating itself could actually be something far more ordinary. Triangulum 2 is one of the faintest galaxies in the local group, with just a few thousand stars. If it weren't for its strange gamma-ray signal, we might have overlooked it entirely. Gamma rays are the universe's highest energy light, usually produced by extreme events like supernova or colliding neutron stars. But in this case, the gamma rays coming from Triangulum 2 don't match any known astrophysical source. Instead, they cluster near the galaxy's center, exactly where dark matter should be densest. This odd alignment has led some researchers to propose a thrilling possibility. these gamma rays could be the smoking gun of dark matter annihilation. According to certain theories, dark matter particles might occasionally collide and destroy each other, releasing energy as gamma rays. If true, Triangulum 2 could be the first place we've spotted this process in action. Imagine a tiny, dim galaxy acting as a laboratory for uncovering the invisible fabric of the cosmos. But before we rewrite the textbooks, there's a catch. Not everyone's convinced these gamma rays come from dark matter. Another camp argues they could just be the work of pulsars, rapidly spinning neutron stars that shoot out beams of radiation like cosmic lighthouses. Pulsars are common throughout galaxies, and some emit gamma rays. The problem, Triangulum 2 is so faint, we can't yet spot individual pulsars within it to confirm or rule them out. The debate gets even thornier when you compare Triangulum 2 to other galaxies. Take Reticulum 2, another ultra-faint dwarf in the local group. It also emits excess gamma rays, but unlike Triangulum 2, its signal isn't as neatly centered. Some scientists see this as evidence that Reticulum 2's gamma rays come from pulsars, since pulsars can wander from a galaxy's core. If that's true, maybe Triangulum 2's signal is just a coincidence, a handful of pulsars huddled near its center by chance. Then there's the dark matter distribution itself. Simulations predict that small galaxies like Triangulum 2 should have dense, peaked dark matter cores. If dark matter is annihilating, the gamma rays should follow that same concentrated pattern, exactly what we see. But critics point out that our simulations aren't perfect. Tiny errors in modeling how dark matter clumps could make us see signals where none exist. So where does that leave us for now? Triangulum 2 is a tantalizing maybe. New telescopes like the upcoming Cherenkov telescope array could settle the debate by detecting finer details in the gamma ray signal. If the light's energy spectrum matches dark matter predictions, that's a huge win. If it looks more like pulsars, the mystery deepens. Regardless of the outcome, Triangulum 2 teaches us something vital. The universe's faintest, most overlooked corners can harbor the most profound secrets. Whether it's dark matter or pulsars, this little galaxy reminds us that big discoveries often come in small packages. Next up, we'll unravel the story of the Cetus dwarf, a galaxy with not one, but two distinct populations of stars, each telling a different tale about its turbulent past. How did these stellar groups end up sharing the same space? The clues are written in their light. Shifting our gaze to another small but fascinating member of the local group, we find the Cetus dwarf, a galaxy that seems to be living two lives at once. While many galaxies have stars of varying ages, the Cetus dwarf stands out because its stars aren't just mixed together. Instead, they're sharply divided into two distinct populations, one ancient and one surprisingly young. This peculiar split has astronomers scratching their heads, wondering what kind of dramatic events could have left such a clear mark on this tiny galaxy. The older stars in the Cetus dwarf are typical of what you'd expect in a small, isolated galaxy. They're metal-poor, meaning they formed early in the universe's history when heavier elements were scarce. These stars are faint, red, and scattered loosely across the galaxy, hinting at a quiet, uneventful past. But then there's the second group, young, blue stars that blaze brightly, clustered in tight formations. These shouldn't exist in a galaxy like this, at least not according to traditional models. Small, faint galaxies like the Cetus dwarf usually run out of gas early in their lives, leaving them unable to form new stars for billions of years. So how did this one manage to reignite star formation long after it should have gone dormant? The answer might lie in a violent encounter millions of years ago. One leading theory suggests the Cetus dwarf collided with another small galaxy, funneling fresh gas into its core and triggering a burst of new star formation. Color magnitude diagrams, a tool astronomers use to compare stars' brightness and color, reveal this stark division clearly. the older stars form a broad, faint band, while the younger stars create a sharp, bright sequence offset from the rest. This isn't just a minor variation, it's evidence of two separate epochs of star formation, separated by a long, silent gap. But mergers aren't the only possible explanation. Some researchers argue that the Cetus dwarf might have slowly accumulated gas over time, perhaps stealing it from intergalactic space or pulling it in from a nearby filament of the cosmic web. If that gas pooled in the galaxy's center, it could have sparked a late wave of star birth without the need for a collision. However, this scenario struggles to explain why the young stars are so tightly concentrated, a pattern that usually points to a sudden, disruptive event. Adding to the mystery, the Cetus dwarf isn't the only galaxy with dual populations. The Carina dwarf, another local group member, shows a similar split, but with a crucial difference: its star-forming periods were spaced out more evenly. This suggests that while multiple mechanisms can create dual populations, the Cetus dwarf's extreme gap points to something more catastrophic. So what's the takeaway? The Cetus dwarf forces us to rethink how small galaxies evolve. Instead of fading quietly into the cosmic background, some of these faint systems might have dramatic, even violent histories hidden in their starlight. Whether through collisions, gas theft, or some other process we haven't yet imagined, galaxies like this one remind us that even the smallest players in the local group have stories worth telling. Up next, we turn to the Leo T dwarf, a galaxy that defied expectations by waiting until the universe was nearly middle-aged before forming its first stars. What made it hit the snooze button for so long? The answer might change how we understand the quietest corners of the cosmos. Now, let's journey to one of the most puzzling late bloomers in the local group, the Leo T dwarf. While most galaxies were busy forming stars in the universe's fiery youth, this tiny dwarf galaxy decided to take its time waiting until the cosmos was nearly half its current age before lighting up with its first stellar generation. What made Leo T hit the cosmic snooze button for so long? The answer might rewrite our understanding of how the faintest galaxies evolve. Unlike the Cetus dwarf with its dramatic split personalities, Leo T is a study in patience. Most dwarf galaxies in the local group formed the bulk of their stars over 10 billion years ago, during the universe's early, gas-rich frenzy, but Leo T. It barely got started around 1 billion years ago, a staggeringly late debut. Even more intriguing, it's still forming stars today, albeit at a snail's pace. This makes it a rare living laboratory for studying how low-mass galaxies ignite star formation under extreme conditions. So why the delay? The key lies in Leo T's gas reservoir, or more precisely, its lack of density. While other dwarfs burned through their gas quickly, Leo T's supply was so thinly spread that gravity couldn't easily collapse it into star-forming clouds. Imagine trying to light a campfire with damp kindling. The materials are there, but conditions aren't right for ignition. For billions of years, Leo T's gas simply drifted, too diffuse to trigger the birth of stars. But something changed. One theory suggests that the slow accumulation of gas, perhaps from cosmic filaments or a gentle merger, gradually increased the density until pockets reached a critical threshold. Suddenly, the dam broke and the galaxy's first stars flickered to life. Supporting this idea, observations reveal that Leo T's stars are clustered in a few small, bright knots embedded within a vast, faint halo of neutral hydrogen. This lopsided distribution hints at a gas supply that's only recently become dense enough to sustain star formation in localized bursts. Another clue comes from Leo T's environment. Unlike many dwarfs orbiting the Milky Way or Andromeda, Leo T is relatively isolated. This means it avoided the gravitational harassment that strips gas from satellites, leaving it free to hoard its fuel over eons. But isolation alone can't explain the timing. Some astronomers propose that cosmic reionization, the era when the universe's first stars and galaxies flooded space with ultraviolet light, might have played a role. Early on, this radiation could have heated Leo-T's gas, preventing it from cooling and collapsing. Only much later, as the universe expanded and cooled, did conditions finally allow star formation to begin. What sets Leo-T apart even further is its mix of stars. Unlike the Cetus dwarf's stark divisions, Leo-T's stellar population is remarkably uniform in age, with no ancient stars in sight. This suggests it truly is a latecomer, missing the universe's early star-forming parties entirely. Yet, it's not entirely pristine. Deep imaging has uncovered a handful of older, redder stars, perhaps captured from another galaxy or the faint remnants of an earlier, failed attempt at star birth. The implications are profound. If galaxies like Leo-T can lie dormant for billions of years before awakening, it means the cosmic story of star formation isn't as uniform as we once thought. There might be countless other sleeping dwarfs lurking in the local group, waiting for the right conditions to spark to life. It also challenges models of galaxy evolution, which often assume low-mass dwarfs form their stars early or not at all. Leo-T proves that the rules aren't so simple. As we move forward, keep this in mind: the universe loves exceptions. Just when we think we've figured out the pattern, galaxies like Leo-T remind us that cosmic history is full of surprises. Up next, we'll explore another rebel, the Phoenix Dwarf, a galaxy that didn't just delay star formation but stopped entirely, only to spectacularly reboot itself millions of years later. How that's a story of resilience written in starlight. Now, let's meet a cosmic phoenix, the Phoenix Dwarf Galaxy, a place where starbirth defied the odds by rising from the ashes after billions of years of silence. Unlike Leo-T's slow and steady awakening, the Phoenix Dwarf story is one of resurrection. It's a galaxy that hit pause on star formation entirely, only to spark back to life in a celestial second act. What makes this tiny galaxy so special? For starters, most dwarf galaxies in the local group follow one of two paths. They either burn out early, like the Pegasus dwarf, which shut down star formation 8 billion years ago and never recovered, or they keep forming stars at a steady, if sluggish, pace. The Phoenix Dwarf, though, chose a third way. It stopped, then spectacularly restarted. Here's the puzzle. Observations show that Phoenix's oldest stars date back over 10 billion years, proving it was active in the universe's youth. But then, for reasons still debated, it went quiet. For nearly half the age of the cosmos, this galaxy produced almost no new stars. Its gas lay dormant like embers cooling after a fire. Then, around 1 billion years ago, something reignited the flame. Today, Phoenix hosts vibrant young star clusters alongside its ancient stellar population, a rare case of a galaxy hitting the cosmic reset button. How did this rebirth happen? One clue lies in its gas supply. Unlike quenched dwarfs such as Pegasus, which lost their gas to tidal stripping or reionization, the Phoenix Dwarf held onto a reservoir of neutral hydrogen. This gas lingered, too diffuse to form stars until conditions shifted. Some astronomers suggest a gentle interaction, perhaps a brush with another dwarf, or the inflow of fresh gas from the intergalactic medium, compressed the reservoir just enough to trigger a new wave of star formation. Another factor is location. The Phoenix Dwarf orbits the Milky Way at a relatively safe distance, far enough to avoid the brutal gravitational forces that strip gas from closer satellites like the Sagittarius dwarf. Yet it's not entirely isolated. Its position may have allowed it to siphon gas from cosmic filaments over time, gradually replenishing its fuel. The galaxy's name couldn't be more fitting. Like the mythical bird, it embodies renewal. Hubble images reveal bright blue knots of young stars nestled within a rusty glow of older stellar populations, a visible timeline of its explosive past and vibrant present. Even more intriguing, these young stars aren't randomly scattered. They're concentrated in the galaxy's outer regions, suggesting the rebirth began at the edges and may still be spreading inward. What does this mean for our understanding of galaxies? Phoenix challenges the idea that star formation is a one-way street toward shutdown. Instead, it proves that under the right conditions, even the smallest galaxies can stage comebacks. This has huge implications for the hunt for dark matter, too. Many models assume dwarf galaxies lose their gas and stop forming stars early, but Phoenix's resurgence suggests some may retain enough dark matter to eventually pull gas back into star-forming mode. The contrast with galaxies like Pegasus is striking. Both started with similar gas-rich conditions, but where Pegasus succumbed to external pressures, Phoenix found a way to bounce back. Studying these two side by side helps astronomers piece together why some dwarfs fade while others flicker back to life. As we close this chapter, remember, the universe loves a good plot twist. Just when we think we've mapped the life cycles of galaxies, outliers like the Phoenix dwarf rewrite the script. Next up, we'll encounter Andromeda 12, a galaxy moving so fast it might be fleeing the local group altogether. What launched this cosmic speedster? The answer could reveal hidden forces shaping our galactic neighborhood. Now, let's shift gears to a cosmic speedster, Andromeda 12, a galaxy moving so fast it's practically on its way out of the local group. If galaxies had passports, this one would be stamped with "exiting soon." Unlike the Phoenix dwarf's story of rebirth, Andromeda 12's tale is one of sheer velocity, and it's rewriting what we know about galactic motion. What makes this galaxy so extraordinary? Its speed. Andromeda 12 is racing away at nearly 400 kilometers per second, so fast that it's likely already escaped the gravitational pull of the local group. To put that in perspective, most galaxies in our neighborhood orbit each other at a leisurely pace, bound by gravity like dancers in a slow waltz, but Andromeda 12. It's more like a bullet fired into the void. So how did it get this boost? The leading theory is that Andromeda 12 is what astronomers call a backsplash galaxy. Imagine it as a cosmic slingshot victim. Billions of years ago, it might have fallen toward the heart of the local group, passing near massive galaxies like Andromeda or the Milky Way. Their gravity would have yanked it inward, then flung it back out with even greater speed, like a pendulum swinging to its peak and then hurtling backward. Now it's on its way to intergalactic space, a rare case of a galaxy getting evicted from its home. But here's the twist: backsplash galaxies shouldn't be this fast. Simulations predict they'd move quickly, but Andromeda 12's velocity is off the charts. Some researchers argue that dark matter might be the unseen hand behind this extreme acceleration. If the local group's dark matter halo is denser or more uneven than we thought, it could have given Andromeda 12 an extra kick. Others speculate that the galaxy might have had a close encounter with another massive object, one we haven't spotted yet, that sent it flying. What's even more puzzling is its isolation. Most high-speed galaxies show signs of recent interactions, tidal tails, distorted shapes, or missing gas. But Andromeda 12 looks oddly pristine. Its stars are calmly orbiting, and its structure is intact, as if it never went through the gravitational chaos that should have accompanied such a dramatic journey. This has led to a heated debate. Is it truly a backsplash galaxy, or did something else propel it? One bold hypothesis suggests it could be an intruder from another galaxy group passing through ours by chance. The stakes are high for understanding galactic evolution. If Andromeda 12 is a backsplash galaxy, its extreme speed implies the local group's gravity is stronger than we realized, which would mean there's more mass, likely dark matter, hiding in our cosmic backyard. If it's an interloper, it challenges our assumptions about how often galaxies wander between groups. Either way, this speedster is forcing astronomers to rethink their models. Andromeda 12 also raises a tantalizing question. How many other galaxies like it are out there? Current telescopes might miss ultra-fast, faint galaxies, especially if they're already far beyond the local group. Future observatories like the Nancy Grace Roman Space Telescope could hunt for more of these cosmic runaways, revealing whether Andromeda 12 is a freak accident or part of a larger pattern. As we watch this galactic fugitive flee, it's a reminder that the universe is full of surprises. Just when we think we've mapped the rules of motion, outliers like Andromeda 12 come along and break them. Next up, we'll turn our attention to another rebel NGC 185, a dwarf galaxy with a hidden quasar past. What scars did its explosive youth leave behind? The clues are written in ancient jets and radio whispers. Now, let's step into the shadows of the past to uncover the secrets of NGC 185, a dwarf galaxy with a surprisingly explosive history. While many small galaxies live quiet, uneventful lives, this one is like a retired rebel, its faded scars hinting at a youth far more violent than its calm appearance suggests. What sets NGC 185 apart are the faint but unmistakable signs of its turbulent past, jets and radio lobes stretching far beyond its boundaries. These ghostly structures are the fingerprints of a supermassive black hole that once raged at its core, feasting on gas and spewing energy in a fiery display. Today, the black hole is silent, but the remnants of its activity linger like echoes in the void. Jets and radio lobes are typically the calling cards of quasars, the blazing cores of galaxies where supermassive black holes devour matter and unleash torrents of radiation. But quasars are usually found in massive galaxies, not unassuming dwarfs like NGC 185. So how did this petite galaxy end up with such dramatic features? The answer lies in its history. Billions of years ago, NGC 185 likely had a brief but intense phase of black hole activity. A sudden influx of gas, perhaps from a collision with another galaxy or a destabilized gas cloud, could have triggered the black hole to awaken, transforming it into a miniature quasar. For a cosmic blink, it would have shone brightly, its jets carving through space before the fuel ran out and the lights dimmed. What makes this even more intriguing is how different NGC 185 is from its so-called twin, NGC 147. These two galaxies orbit Andromeda together, similar in size and composition, yet one has a hidden wild side while the other is the picture of serenity. NGC 147 shows no signs of past eruptions, no jets, no radio lobes, just a quiet existence. Why the stark contrast? One possibility is that NGC 185 had a close encounter with another galaxy or a dense gas cloud, something NGC 147 avoided. Another theory suggests that their central black holes might have behaved differently, one voraciously feeding, the other starving. The mystery deepens when we consider their globular clusters. NGC 185 has several ancient star clusters, while NGC 147 has none. Some astronomers speculate that the same violent events that fueled its black hole may have also disrupted or destroyed NGC 147's clusters. Others argue that the twins might have formed under different conditions, their fates diverging early on. But NGC 185 isn't just a relic, it's a clue. Its existence challenges the assumption that only massive galaxies can host powerful quasars. If a small galaxy like this once blazed like a cosmic beacon, how many others did the same, their traces now too faint to detect? It also raises questions about black hole growth. Did its central black hole start unusually massive, or did it grow quickly during its active phase? Studying galaxies like NGC 185 helps us piece together the chaotic early universe when black holes and galaxies grew side by side in a frenzy of collisions and feasting. Its quiet present hides a dramatic past, reminding us that even the smallest galaxies can have grand stories to tell. Up next, we'll turn to IC 1613, a galaxy so pristine it's helped astronomers measure cosmic distances with astonishing precision. How did this unassuming dwarf become a ruler for the universe? The answer lies in its crystal-clear hydrogen clouds. Now, let's shift our gaze to IC 1613, a galaxy that might not look like much at first glance, but holds a secret that makes it one of the most valuable tools in the astronomer's toolkit. Nestled in the constellation Cetus, this unassuming dwarf galaxy has given scientists something rare and precious, an almost perfect cosmic yardstick. What makes IC 1613 so special is its remarkably clean hydrogen gas. Unlike many galaxies where dust and heavy elements obscure our view, this one is nearly transparent, offering astronomers an unobstructed look at the celestial objects inside it. This clarity is key because it allows us to spot certain pulsating stars called Cepheids variables with extraordinary precision. Cepheids are cosmic lighthouses. Their brightness changes at a rate directly tied to their true luminosity, meaning if we measure their pulse, we can calculate their distance. But in most galaxies, dust dims their light, skewing the measurements. Here, the pristine conditions remove that problem entirely. Thanks to this cleanliness, astronomers have pinned down IC 1613's distance to within just 1% accuracy, an astonishing feat when dealing with objects millions of light-years away. To put that in perspective, imagine measuring the distance from New York to Los Angeles with an error margin of just a few feet. This precision makes the galaxy a cornerstone for calibrating the cosmic distance ladder, the series of methods astronomers use to measure the scale of the universe. Without benchmarks like IC 1613, our understanding of distances to faraway galaxies, and by extension, the expansion rate of the universe, would be far less certain. But how did this galaxy stay so clean? The answer lies in its lack of heavy elements, or what astronomers call low metallicity. Unlike the Milky Way, which is enriched with elements forged in generations of stars, IC 1613 has remained relatively unpolluted. Its stars are made mostly of hydrogen and helium, the raw materials of the early universe. This simplicity means less dust, fewer obstructions, and clearer sightlines, perfect conditions for precise measurements. Interestingly, IC 1613's role in cosmic distance measurements isn't just about convenience. It's also about resolving one of astronomy's biggest headaches, the Hubble tension. This is the puzzling discrepancy between different methods of measuring the universe's expansion rate. By providing such a precise anchor point, this galaxy helps scientists cross-check their numbers, bringing us closer to solving the mystery. Beyond its scientific value, IC 1613 also tells a story of cosmic evolution. Its pristine state suggests it's lived a relatively quiet life, avoiding major mergers or bursts of star formation that would have polluted its gas. That isolation makes it a living fossil, a snapshot of what many galaxies might have looked like billions of years ago. Yet despite its quiet nature, this galaxy has had an outsized impact. It reminds us that sometimes the most unremarkable-looking objects hold the keys to the universe's biggest questions. And as astronomers continue to refine their measurements, IC 1613 will remain a trusted guide in the vast and often murky cosmic ocean. Next, we'll venture into the realm of dark matter with the Sexton's Dwarf, a galaxy whose strange, soft core profile is stirring up debates about the very nature of this invisible cosmic glue. Why does this tiny galaxy defy expectations, and what could it mean for our understanding of the universe's hidden scaffolding? The answers might just rewrite the rules. Turning our attention to the enigmatic Sexton's Dwarf, we encounter a galaxy that's stirring up quite the cosmic controversy. This unassuming satellite of the Milky Way might appear ordinary at first glance, but its dark matter profile is anything but challenging long-held theories and leaving scientists scrambling for explanations. The Sexton's Dwarf belongs to a class of galaxies that are supposed to be dominated by dark matter, the invisible glue that holds the universe together. But here's the twist. While most dwarf galaxies have dense, cuspy dark matter cores, meaning the dark matter piles up intensely toward the center, Sextans has an oddly soft core. Its dark matter is distributed more evenly, almost like a fluffy cloud rather than a concentrated knot. This directly contradicts predictions made by the leading cold dark matter model, which has been the backbone of our understanding of cosmic structure for decades. So why does this matter? Cold dark matter theory suggests that dark matter particles are slow-moving and cold, clumping together to form dense halos around galaxies. Yet sextans and a handful of other dwarfs refuse to play by these rules. Their soft cores suggest something else is at work. Perhaps dark matter isn't as simple as we thought. One compelling alternative is the idea of self-interacting dark matter. Unlike cold dark matter, which barely notices its own existence, self-interacting particles could collide and scatter, smoothing out the dense cusps into the gentler profiles we see in sextans. But the plot thickens. Another possibility is that the gravitational pull of the Milky Way has somehow reshaped sextans' dark matter halo over billions of years. Tidal forces, the same kind that create ocean tides on Earth, could have stretched and stirred the dwarf's core, diluting its central density. However, simulations show that while tides can distort a galaxy's outer regions, they struggle to explain the full extent of sextans' soft core. That leaves scientists questioning whether we're missing a crucial piece of the puzzle. What makes sextans particularly fascinating is its stellar motions. Stars in this dwarf move more sluggishly than expected if it were anchored by a dense dark matter cusp. Instead, their orbits align better with a fluffier distribution. This discrepancy is like finding a car moving at half the speed its engine should allow. Something unseen is at play. Some researchers argue that feedback from ancient supernova could have blown gas outward, dragging dark matter with it and puffing up the core. But even this idea struggles to fully account for sextans' peculiarities. The debate over sextans isn't just academic, it strikes at the heart of our understanding of the universe's hidden architecture. If cold dark matter needs revising, it could affect everything from galaxy formation to the fate of the cosmos. Self-interacting dark matter isn't the only alternative. Theories like warm dark matter with faster-moving particles or even modified gravity have been proposed. Yet none perfectly explain all the observations, leaving astronomers in a tantalizing loop of mystery and discovery. Beyond the science, sextans serves as a humbling reminder. Even our best models are provisional, subject to revision by the next oddball galaxy that refuses to conform. Whether its soft core points to new dark matter physics or an overlooked astrophysical process, one thing's certain: this tiny galaxy is punching far above its weight in cosmic significance. Now let's journey to Andromeda 21, where a colossal arc of stars tells a dramatic tale of galactic collisions and gravitational upheaval. What secrets lie in this stellar stream, and how did it come to stretch across the cosmos? The story is written in the stars, we just have to decode it. Now, drifting toward the outskirts of the Andromeda Galaxy, we uncover a celestial masterpiece written in starlight, the sprawling stellar stream of Andromeda 21. This vast, curving ribbon of stars stretches tens of thousands of light-years across space, a ghostly remnant of a violent encounter frozen in time. Unlike the neat, symmetrical spirals we often picture when imagining galaxies, Andromeda 21 is a cosmic scribble, its stars scattered in a chaotic arc that defies the usual rules of galactic structure. So what caused this spectacular disruption? The leading theory points to a dramatic collision. A smaller galaxy, perhaps a dwarf like those we've explored earlier, strayed too close to Andromeda's gravitational grasp. Over billions of years, the relentless tidal forces stretched and shredded the intruder, pulling its stars into this elongated stream. Imagine twirling a spoon in honey. The way the liquid stretches into long threads mirrors how gravity sculpts these stellar rivers. But Andromeda 21's stream isn't just a random scatter of stars. Detailed observations reveal subtle clues about its origins. The stream's chemistry is a dead giveaway. its stars are richer in heavy elements like iron compared to the typical halo stars of Andromeda. This suggests the devoured galaxy was no lightweight. It likely had enough mass to forge these metals through generations of supernova before its demise. Some researchers even propose it was a compact, metal-rich dwarf spheroidal galaxy, adding another layer of intrigue to the story. Computer simulations bring this ancient catastrophe to life. By modeling the gravitational interplay between Andromeda and its ill-fated companion, astronomers can rewind the cosmic tape. One compelling scenario shows the dwarf galaxy making multiple close passes, each loop stripping away more stars until all that remains is this glittering trail. The simulations also hint at timing. The merger probably began around 8 billion years ago, making it one of Andromeda's earlier large-scale acquisitions. What's especially fascinating is how the stream's shape encodes secrets about Andromeda's dark matter halo. The way the stars are distributed, their density variations, and the stream's slight kinks acts like a cosmic probe, revealing the invisible gravitational forces at work. Some models suggest the halo might be slightly flattened, not perfectly spherical, which would leave a distinct fingerprint on the stream's structure. This turns Andromeda 21 into more than just a relic. It's a tool for mapping the unseen scaffolding of our galactic neighbor, yet mysteries linger. Why hasn't the stream dissolved entirely after so long? Normally, such structures fray over time, their stars blending into the galactic halo. The fact that this stream remains coherent suggests either the original galaxy was unusually sturdy or Andromeda's halo is smoother than expected, minimizing disruptive turbulence. There's also the curious absence of a visible progenitor, the dense core of the original galaxy, which simulations predict should survive as a compact cluster. Its absence raises questions. Was it entirely disrupted, or is it hiding in plain sight, camouflaged among Andromeda's countless stars? The implications stretch beyond this single event. Andromeda 21 is a textbook example of hierarchical galaxy formation, the idea that galaxies grow by consuming smaller ones. Its stream is a fossil record of Andromeda's violent past, a reminder that even the majestic spirals we admire today were built through chaos. Similar streams have been found around the Milky Way, like the Sagittarius stream, but Andromeda's version offers a unique perspective because we can see it from the outside, unobscured by our own galaxy's dust. This discovery also fuels a broader question. How many more streams are out there, unseen because their stars are too faint? Current telescopes are only beginning to peel back the layers, but next-generation instruments like the Vera Rubin Observatory promise to reveal dozens, if not hundreds, of these structures. Each one could tell a new chapter in the story of galactic evolution. As we marvel at Andromeda 21's stellar arc, we're witnessing more than just a pretty cosmic ribbon. We're seeing evidence of the universe's relentless dynamism, where destruction and creation are two sides of the same coin. This stream is a testament to the fact that even in the vast, seemingly orderly cosmos, chaos leaves its mark, and from that chaos, new structures emerge. Next, we'll venture into the peculiar world of the Pegasus dwarf, a galaxy that hit the cosmic pause button on star formation billions of years ago. What forces could have silenced such a bustling stellar nursery so abruptly? The clues are etched in its ancient stars. Turning our gaze from the grand stellar streams of Andromeda, we encounter a far smaller but equally mesmerizing cosmic oddity, the GR8 dwarf. This unassuming galaxy, tucked away in the local group, holds a peculiar secret. Its star-forming regions are strung across space like pearls on an invisible necklace, defying the usual scattered distribution seen in most dwarf galaxies. At first glance, GR8 appears fragile, a wispy collection of stars and gas adrift in the cosmic void, but peer closer and you'll notice something extraordinary. Its brightest pockets of star formation aren't randomly placed, they're aligned in an almost straight line stretching across the galaxy's length. Astronomers call this the beads on a string formation, and it's one of the clearest examples of such a structure in the known universe. So what forces could arrange star birth so neatly? The answer lies in GR8's turbulent gas clouds. Unlike the Milky Way's orderly spiral arms, where star formation is relatively uniform, this dwarf galaxy's interstellar medium is a battleground of competing forces. Giant waves of gas stirred by supernova explosions or gravitational interactions slam into one another, creating dense ridges where gas piles up like ocean waves meeting a shoreline. These compressed regions become stellar nurseries, and because the turbulence often flows along filamentary structures, the newborn stars cluster into that striking linear pattern. The string itself is likely a massive gas filament, a remnant of the galaxy's chaotic formation. Simulations suggest that when dwarf galaxies assemble, their gas doesn't settle smoothly. Instead, it fragments into long, thread-like structures, and gravity pulls the densest knots along these threads into star-forming hubs. Over time, the brightest knots, the beads, light up while the thinner gas between them fades into the background, leaving this celestial jewelry on display. What makes GR8's beads especially intriguing is their longevity. Normally, such delicate arrangements would be torn apart by the galaxy's own internal motions or external tidal forces. Yet here they persist, hinting at an unusually calm environment. Perhaps GR8 has avoided close encounters with larger galaxies, allowing its delicate structure to endure. Or maybe its dark matter halo is just the right density to cushion the gas from disruptive shocks. Either way, it's a cosmic balancing act that has preserved this rare configuration for millions of years. The beads also offer clues about star formation in the early universe. Dwarf galaxies like GR8 are often considered analogues of the first galaxies, and their simple structures help astronomers test theories about how stars ignited in the cosmic dawn. If turbulence and gas filaments shaped the earliest star-forming regions, then GR8's beads might be a local echo of processes that dominated billions of years ago. But mysteries remain. Why do some gas filaments collapse into beads while others don't? Why does GR8's string appear so straight when turbulence usually creates more tangled patterns? Some researchers speculate magnetic fields play a role, channeling gas flows into orderly lines. Others propose that the galaxy's rotation, though slow, might stretch the filament into its current alignment. One thing is certain, GR8's beads challenge our expectations. We often assume star formation is messy, yet here we see it following an almost artistic arrangement. It's a reminder that even in the vastness of space, patterns emerge from chaos, and sometimes those patterns are as delicate as a string of pearls. Our next stop takes us to the enigmatic Pisces dwarf, a galaxy caught between identities. Is it a lone wanderer, or does it belong to another cosmic family entirely? The answer lies hidden in its starlight. Shifting our cosmic exploration, we land on the enigmatic Pisces dwarf, a galaxy caught in an identity crisis. Is it truly an independent dwarf galaxy, or is it a shredded piece of the Triangulum galaxy, left behind like cosmic debris? This tiny stellar system, hovering on the fringes of the local group, has astronomers divided, and its secrets lie buried in the chemistry of its stars. At first glance, the Pisces dwarf seems unremarkable, a faint smudge of stars barely holding together against the tug of neighboring giants, but its orbit tells a curious tale. Unlike most isolated dwarfs which drift peacefully through the void, the Pisces dwarf follows a path suspiciously close to the Triangulum galaxy, our local group's third largest spiral. Some researchers argue this isn't a coincidence. They propose that the Pisces dwarf might not be a galaxy at all, but a tidal remnant, a cluster of stars ripped from Triangulum's outskirts during a past gravitational encounter. The strongest evidence for this theory comes from metallicity, the cosmic fingerprint of a star's chemical makeup. Stars born from the same gas cloud share similar metallicities, much like siblings share DNA. When astronomers analyzed the Pisces dwarf stars, they found their metal content strikingly similar to Triangulum's outer regions. This overlap suggests a shared origin, as if the Pisces dwarf stars were once part of Triangulum before being torn away. But here's where the debate heats up. Other observations muddy the waters. The Pisces dwarf stars are slightly older and more metal-poor than Triangulum's outermost disk, hinting they might have formed earlier in a separate environment. Additionally, its structure isn't as disordered as typical tidal remnants. If it were debris from a galactic collision, we'd expect its stars to be strewn chaotically. Instead, they cling to a loose but coherent shape, almost as if the dwarf still has some intrinsic gravity holding it together. Then there's the issue of dark matter. True dwarf galaxies are soaked in it, while tidal remnants, having been stripped of their original halo, should have very little. Current measurements of the Pisces dwarf's mass are inconclusive. Some studies detect a faint dark matter signal, others find none. If future observations confirm even a trace, it would bolster the case for it being a genuine dwarf. The mystery deepens when we consider the Pisces dwarf's lonely position. It's not the only disputed galaxy in the local group, but it's one of the few without clear ties to either the Milky Way or Andromeda. If it's a tidal remnant, why isn't it closer to Triangulum? One possibility is that it was flung outward during a three-body interaction, perhaps with Andromeda's gravity playing a role. Another is that it's the sole survivor of a devoured satellite group, left wandering after its siblings were absorbed. The Pisces dwarf forces us to rethink how we classify galaxies. The line between true dwarfs and tidal debris is blurrier than we once assumed. Some astronomers now argue that objects like this exist on a spectrum, where even former pieces of larger galaxies can evolve distinct identities over time. If so, the Pisces dwarf might be both a captured fragment that has, over billions of years, become something new. Up next, we'll examine Andromeda 32, a galaxy stretched so thin by tidal forces that its stars are scattered across an unimaginable volume of space. How does anything remain bound under such conditions? The answer reveals the delicate dance of gravity and time. Now we turn our gaze to Andromeda 27, a galaxy in the throes of destruction. This isn't a slow fade into obscurity, but a violent unraveling, a cosmic ballet where gravity plays the role of both choreographer and executioner. Stretched across 50,000 light-years, Andromeda 27 stars are being ripped from their home, leaving behind a ghostly trail that tells a story of irresistible forces and celestial doom. The scene is haunting. Where most galaxies hold their stars in tidy orbits, Andromeda 27's stellar population is strewn like confetti caught in a cosmic wind. This isn't random chaos, though. The stars follow precise arcs curving along the paths dictated by Andromeda's overwhelming gravity. These aren't just random escapees, they're prisoners in a slow-motion disintegration. Their fate sealed the moment their parent galaxy ventured too close to Andromeda's crushing embrace. What makes this destruction so fascinating is its scale. 50,000 light-years isn't just a measure of distance, it's a timeline. The farthest flung stars in this tidal stream were likely the first to be torn free, their journey beginning hundreds of millions of years ago. Meanwhile, stars closer to the remaining core are only now feeling gravity's relentless pull, their bonds stretching thin like taffy in the hands of a giant. This gives astronomers a rare opportunity. By mapping the stream's density and structure, they can essentially rewind the destruction, piecing together not just how Andromeda 27 is dying, but how it once lived. The evidence for this tidal disruption is overwhelming. First, there's the sheer elongation of the galaxy itself. No intact dwarf galaxy stretches 50,000 light-years. Then there's the velocity of its stars. Measurements show them moving at different speeds, some accelerating toward Andromeda, others drifting away, all following the predicted paths of a system coming apart at the seams. Most damning of all is the absence of a dark matter halo. dwarf galaxies typically cling to massive shrouds of dark matter, but Andromeda 27's ghostly stream shows no such anchor. This suggests it's already been stripped down to bare stars, the invisible scaffolding of its existence long since scavenged by Andromeda's gravitational pull. Yet amid this destruction, there's a puzzle. Some stars in the stream are clumped together in unexpected ways. Normally, tidal forces should scatter stars evenly like sand thrown into the wind. But certain patches of the stream show higher densities, almost as if remnants of the original galaxy's structure are stubbornly holding on. One theory suggests these could be the cores of globular clusters, tightly bound families of stars that resist disruption longer than their looser neighbors. Another possibility is that they're evidence of multiple disruption events, with Andromeda 27 having endured not one gravitational assault, but several over billions of years. The fate of Andromeda 27 is a preview of our own galaxy's distant future. When the Milky Way and Andromeda collide in 4 billion years, similar tidal forces will tear at both giants, reshaping them into something new. In a way, Andromeda 27 is both a victim and a messenger, an omen of the chaos that awaits when galaxies meet. Next, we'll encounter UGC 4879, a galaxy so isolated it's earned the nickname the Hermit of the local group. How does a galaxy survive and even thrive in near total solitude? The answer reveals just how resourceful the cosmos can be. Leaving behind the violent unraveling of Andromeda 27, we now venture into the profound loneliness of the cosmos, where UGC 4879 drifts in near total isolation. Imagine a single house standing in the middle of an endless desert with no neighbors in sight. That's UGC 4879, a galaxy so remote it's often called the hermit of the local group. While most galaxies cluster together like bustling cities, this dwarf galaxy floats 2.3 million light-years from its nearest significant neighbor, an almost unimaginable distance. To put that into perspective, that's over 10 times the span between the Milky Way and Andromeda. How does a galaxy survive in such emptiness? The answer lies in its stubborn self-sufficiency. Unlike galaxies in denser regions, which often steal gas from neighbors or collide to trigger star formation, UGC 4879 has had to rely entirely on its own reserves. Yet somehow, against all odds, it hasn't just survived, it's thrived in fits and starts. Observations reveal pockets of young, blue stars, proof that star formation has flickered on and off over billions of years. This sporadic activity is a puzzle. Normally, isolated galaxies either exhaust their gas quickly in a burst of early star formation or fade into quiet obscurity. But UGC 4879 has managed to hold onto just enough gas to reignite star birth multiple times, like a campfire that somehow keeps smoldering despite the wind. One theory suggests its gas might be trapped in a delicate balance too sparse to collapse into stars easily, but not so thin that it completely evaporates into intergalactic space. Another idea points to its quiet environment. Without the gravitational jostling of nearby galaxies, its gas hasn't been stripped away or stirred into frenzied star-forming bursts. Instead, it lingers in a slow, almost meditative rhythm, collapsing into stars only when conditions are just right. There's also the possibility that UGC 4879 isn't as alone as it seems. Some astronomers speculate it could be accompanied by tiny, unseen companions, dim galaxies or dark matter clumps that occasionally nudge its gas reservoirs, triggering new stellar generations. What makes this galaxy even more intriguing is its resemblance to the universe's earliest galaxies. Its slow, intermittent star formation and pristine gas content mirror conditions from billions of years ago, when the cosmos was younger and galaxies were fewer and farther between. In a way, UGC 4879 is a living fossil, offering a glimpse into a time before galactic neighborhoods became crowded. Yet its isolation raises a deeper question: how did it end up so alone in the first place? One possibility is that it was flung outward during the local group's chaotic early interactions, like a stone hurled from a spinning sling. Another is that it formed in place, emerging from a rare overdensity in the cosmic web that simply never connected to larger structures. Either way, its existence challenges our understanding of how galaxies form and persist. Most models predict that galaxies this small shouldn't last long in isolation, yet here it is, defying expectations. As we move forward, the mysteries only deepen. Next, we'll examine Andromeda 34, a galaxy with a dark matter profile that stands in stark contrast to everything we've seen so far. How can two dwarf galaxies in the same group be so fundamentally different? The answer might rewrite what we know about the invisible scaffolding of the cosmos. Now, shifting our gaze from the lonely outpost of UGC 4879, we arrive at a cosmic oddity that defies expectations in the opposite way: Andromeda 17, a dwarf galaxy that seems to be missing something vital. Where most galaxies, even the smallest ones, are anchored by vast halos of dark matter, Andromeda 17 appears almost bare, its stars moving sluggishly as if gravity itself is barely holding them together. This isn't just unusual, it's a direct contradiction to what we see in galaxies like Leo 1, another dwarf in the local group that's drowning in dark matter. How can two galaxies, neighbors in the same cosmic neighborhood, be so fundamentally different? Let's start with the numbers. Observations suggest Andromeda 17's dark matter content is shockingly low. Some estimates put it at less than 10% of what typical dwarf galaxies hold. Compare that to Leo 1, which is nearly 99% dark matter by mass, with stars whipping around at speeds that shouldn't be possible without that invisible anchor. The disparity is staggering. It's like finding two cars side by side, one with an engine, the other rolling downhill without one, and being told they both drove here under their own power. Astronomers are left scratching their heads. If dark matter is as universal as we believe, why does Andromeda 17 seem to have lost the cosmic lottery? One possibility is that Andromeda 17 was stripped of its dark matter long ago. Picture a galaxy wandering too close to Andromeda's immense gravitational pull, its outer layers of dark matter sheared away by tidal forces, leaving only the visible stars behind. This might explain its wispy, diffuse appearance, like a tree that's lost its roots, barely standing. But there's a problem with this idea. Other galaxies that have undergone tidal stripping, like Andromeda 27, show clear signs of disruption: tidal tails, distorted shapes, or streams of stars. Andromeda 17, though, looks oddly intact with no obvious scars from a violent past. So if it wasn't torn apart, where did its dark matter go? Another theory takes a different approach. Maybe Andromeda 17 never had much dark matter to begin with. Some simulations suggest that certain dwarf galaxies could form with naturally low dark matter content, particularly in regions where the cosmic web is sparse or tangled. If true, this would upend our understanding of galaxy formation, which assumes dark matter is the seed around which all galaxies grow, but proving this is tricky. Without a clear mechanism to explain how a galaxy could skip the dark matter step, the idea remains on the fringe. Then there's Leo 1, Andromeda 17's polar opposite. This tiny galaxy's stars move so fast that, without its enormous dark matter halo, they should have flown apart eons ago. Why does Leo 1 cling to so much dark matter while Andromeda 17 has so little? One clue might lie in their orbits. Leo 1 skirts the far edges of the local group, a cosmic recluse that's avoided close encounters with larger galaxies. Andromeda 17, on the other hand, orbits much closer to Andromeda, where gravitational interactions could have played a role in its dark matter deficit. But even this doesn't fully explain the extreme mismatch. The mystery deepens when we consider that both galaxies are roughly the same size and age. They should, by all accounts, be cut from the same cloth. Yet their differences are impossible to ignore. This isn't just a quirk. It's a challenge to the very frameworks we use to understand galaxy evolution. If dark matter isn't distributed as predictably as we thought, what else might we be missing? As we prepare to delve into the next enigma, keep this question in mind. The local group is full of surprises, and each one forces us to rethink what we know. Up next, we'll explore another twist in the dark matter saga, one that might reveal even more about the hidden forces shaping our cosmic backyard. Now, let's turn our attention to a ghostly echo of the past, the Pegasus Dig galaxy and its haunting remnants of stellar fury. Unlike the dark matter mysteries we just explored, this dwarf galaxy holds clues to a different kind of cosmic enigma, the fossilized remains of its once vibrant star-forming regions. Imagine stumbling upon the ruins of an ancient civilization, but instead of crumbling stone, these are delicate, glowing bubbles of gas, vestiges of massive stars that lived fast, died young, and left behind only whispers of their existence. The Pegasus Dig, short for Pegasus Dwarf Irregular Galaxy, is a small, unassuming neighbor in the local group, but hidden within its faint glow are what astronomers call fossil H2 regions, ancient pockets of ionized hydrogen gas. These bubbles were once the stellar nurseries of massive, short-lived stars, whose intense radiation lit up the surrounding gas like neon signs. But here's the twist: those stars are long gone, having exploded as supernova or faded into oblivion millions of years ago. All that remains are these faint, ghostly wisps, still glowing faintly from the energy those stars poured into them long after their deaths. What makes these fossil H2 regions so fascinating is their longevity. Normally, when massive stars die, their violent ends, supernova or powerful stellar winds, blow away the surrounding gas, dispersing it into space. But in Pegasus Dig, these bubbles have persisted, lingering like cosmic smoke rings. It's as if the galaxy forgot to clean up after its stellar fireworks. Astronomers suspect this could be due to the galaxy's low density. With fewer stars and weaker gravity, there's nothing to disrupt these fragile structures, allowing them to hang around far longer than they would in a bustling galaxy like the Milky Way. To put it in perspective, think of a campfire. In a windy forest, the embers scatter quickly, but in a sheltered corner, the ashes might stay intact for hours. Pegasus Dig is that sheltered corner, a quiet backwater where these ancient gas bubbles can survive undisturbed. Observations from telescopes like the Hubble Space Telescope reveal these structures as faint, irregular blobs, some stretching hundreds of light-years across. Their shapes tell stories of the stars that created them. Some are spherical, suggesting a single massive star's influence, while others are twisted or elongated, hinting at turbulent past shaped by multiple stellar generations. But why does this matter? These fossil regions are more than just celestial curiosities. They're cosmic time capsules preserving information about the galaxy's star-forming history. By studying them, astronomers can piece together how often Pegasus Dig gave birth to massive stars, how those stars shaped their surroundings, and even how the galaxy's environment, its lack of nearby disruptive forces, allowed these relics to survive. It's like finding a prehistoric insect trapped in amber, frozen in perfect detail. What's even more intriguing is how rare these structures are. Most dwarf galaxies are either too chaotic, with ongoing star formation churning up their gas, or too quiet, with no massive stars to create such bubbles in the first place. Pegasus Dig occupies a sweet spot. It had just enough activity in the past to create these fossils, but not enough to erase them. That balance makes it a unique laboratory for understanding the life cycles of stars in isolated environments. As we move forward, remember that the local group isn't just a collection of galaxies, it's a graveyard of forgotten stellar eras, a museum of cosmic history written in gas and light. Next, we'll uncover another relic, one that tells a story of delayed cosmic evolution and a galaxy that refused to follow the rules. Now, let's journey to a galaxy that seems to defy time itself, the Leo, a dwarf. While most galaxies show their age with older, redder stars, Leo A looks astonishingly young, bursting with blue stars and fresh stellar activity. But here's the catch: this galaxy is nearly as old as the universe. So why does it act like a cosmic teenager? The answer lies in its sluggish gas accretion and a life spent on the sidelines of galactic drama. Leo A is a tiny, isolated dwarf galaxy in the local group, floating about 2.5 million light-years away. At first glance, it looks like a late bloomer. Its skies are filled with bright blue stars, which typically indicate recent star formation, and it's even had a few bursts of stellar births in the last billion years. But here's the twist: Leo A isn't young. In fact, it's been around for roughly 13 billion years, almost as long as the cosmos itself. This mismatch between its age and its youthful appearance makes it one of the most puzzling objects in our galactic neighborhood. So how does a galaxy this old stay so fresh? The secret lies in its slow and steady diet of gas. Unlike bustling galaxies like the Milky Way, which constantly pull in gas from their surroundings to fuel star formation, Leo A has had a much quieter existence. It's spent eons drifting in relative isolation, far from the gravitational tugs of larger galaxies that might have disrupted it or stolen its gas. Because of this, Leo A has only occasionally gathered enough gas to spark new stars, leading to sporadic bursts of activity rather than a continuous firestorm of stellar births. Imagine a campfire that's been burning for hours, but instead of roaring steadily, it flickers to life only when someone occasionally tosses on another log. That's Leo A galaxy that's been around forever but only lights up when it gets a fresh supply of fuel. Telescopes like Hubble have spotted multiple generations of stars here, with the youngest blue stars standing out against a backdrop of much older ones. This patchwork of stellar ages tells us that Leo A didn't form all its stars at once, but instead in fits and starts, whenever enough gas drifted into its grasp. Another clue to its delayed evolution comes from its metal content, or rather, the lack of it. In astronomy, metals refer to any elements heavier than hydrogen and helium, and they're produced by stars over time. Leo A has remarkably low metallicity, meaning it hasn't hosted many generations of stars to enrich its gas. This further supports the idea that it's been forming stars slowly and sporadically, never going through the rapid, metal-producing cycles of more active galaxies. But why does this matter? Leo A gives us a rare glimpse into how galaxies behave when they're left alone, untouched by the chaos of collisions or the theft of their gas by larger neighbors. It's a living time capsule, showing us what the universe's smaller galaxies might have looked like if they'd evolved in isolation. By studying its star-forming history, astronomers can test theories about how gas accretion shapes galaxy evolution, especially in the quiet corners of the cosmos. What's even more intriguing is how Leo A contrasts with other dwarf galaxies. Many of its peers, like the Pegasus dig we just discussed, have either burned through their gas long ago or had it stripped away by larger galaxies. But Leo A has held onto its gas tenaciously, allowing it to keep forming stars at its own leisurely pace. This makes it a unique laboratory for understanding how galaxies can resist the typical aging process, staying young, even as the universe grows old around them. As we move forward, remember that the local group isn't just a collection of galaxies, it's a tapestry of unique life stories, each with its own rhythm and pace. Next, we'll explore another oddball galaxy, one that orbits in the opposite direction of its neighbors, defying expectations yet again. Now, let's turn our attention to a galaxy that dances to its own rhythm, Andromeda 29. This peculiar dwarf galaxy has a stellar population that moves in the exact opposite direction of Andromeda's rotation, like a cosmic rebel defying the flow of traffic. This backward motion isn't just a random quirk, it's a clue pointing to a dramatic past where this galaxy may have been captured by Andromeda's gravity after a cosmic showdown billions of years ago. Nestled within Andromeda's vast halo, Andromeda 29 stands out because its stars orbit in a direction that's completely at odds with the spin of its massive neighbor. Picture a group of cars driving the wrong way on a highway. That's essentially what's happening here. Most satellite galaxies, like those orbiting the Milky Way, move in the same direction as their host galaxy's rotation. But Andromeda 29 bucks this trend, suggesting it wasn't born alongside Andromeda, but was instead snatched up later in a gravitational tug of war. Astronomers call this phenomenon retrograde motion, and it's incredibly rare among satellite galaxies. The leading theory is that Andromeda 29 was once part of a different group of galaxies, perhaps a small cluster that wandered too close to Andromeda's gravitational pull. Over time, Andromeda's immense gravity would have torn apart the original group, leaving this lone galaxy spinning backward as a relic of that ancient encounter. What's even more fascinating is that this backward orbit leaves a trail of evidence. As Andromeda 29 moves against the flow, its stars are slowly being stripped away by tidal forces, creating faint streams of stars that curl around Andromeda like cosmic ribbons. These streams, though difficult to detect, are crucial for mapping the galaxy's history. By studying their shape and distribution, astronomers can estimate when and how this galaxy was captured, piecing together a timeline of Andromeda's growth through mergers. But why does this matter? Andromeda 29's rebellious orbit gives us a rare glimpse into how large galaxies like Andromeda and the Milky Way grow. Rather than forming in isolation, they build themselves up by absorbing smaller galaxies over billions of years, a process known as hierarchical assembly. Most of these mergers leave little trace, but Andromeda 29's backward spin is like a fingerprint preserving the memory of its violent past. This galaxy also challenges assumptions about how satellite galaxies behave. Standard models of galaxy formation predict that most satellites should orbit in the same direction as their host's rotation, so finding one that doesn't forces astronomers to rethink how these systems evolve. Was Andromeda 29 an exception, or are there more backward orbiting galaxies we just haven't found yet? The answer could reshape our understanding of galactic dynamics. Adding to the intrigue, Andromeda 29 isn't just moving backward, it's also incredibly faint, making it one of the dimmer satellites in Andromeda's entourage. This suggests it may have already lost much of its original mass to tidal stripping, leaving behind a ghostly remnant of what it once was. Yet, despite its faintness, it's a goldmine of information, offering clues about the unseen dark matter halo surrounding Andromeda and the forces that shaped its evolution. As we continue our tour of the local group's oddities, keep in mind that every galaxy has a story. Some, like Andromeda 29, tell tales of ancient captures and gravitational battles, reminding us that the cosmos is far from static. Next, we'll encounter another enigma, a galaxy that seems to have lost something vital along the way, leaving astronomers scratching their heads. Now, let's unravel another cosmic mystery, one that centers on a pair of galactic twins with a puzzling difference. Meet NGC 147 and NGC 185, two dwarf galaxies orbiting Andromeda that look strikingly similar at first glance. Both are small, faint, and packed with ancient stars, but here's the head-scratcher. NGC 185 hosts several glittering globular clusters, while NGC 147 has none. Why would one twin have these dense star clusters while the other appears to have lost them, or perhaps never had them at all? To understand this oddity, we need to dive into what globular clusters even are. Imagine tight-knit families of hundreds of thousands of stars crammed into a ball just a few dozen light-years wide. These clusters are like fossils from the early universe, often forming alongside their parent galaxies over 10 billion years ago. Most galaxies, even small ones, hold onto at least a few of these ancient stellar relics. So when astronomers noticed NGC 147's complete lack of them, it raised eyebrows. How could a galaxy so similar to its twin, NGC 185, end up so empty-handed? One possibility is that NGC 147 once had globular clusters but lost them along the way. Galactic encounters can be brutal. Tidal forces from a larger galaxy like Andromeda can rip away a dwarf's outer layers, including its clusters. If NGC 147 ventured too close to Andromeda in the past, its clusters might have been stripped away and absorbed into Andromeda's halo. But here's the twist: NGC 185 also orbits Andromeda, yet it still holds onto its clusters. Why would one twin lose everything while the other kept its treasures? This suggests their orbits might have diverged dramatically, with NGC 147 taking a path that exposed it to stronger gravitational harassment. Another theory digs into their formation. Maybe NGC 147 was born in an environment that simply didn't produce globular clusters. These clusters tend to form in regions of dense, turbulent gas. So if NGC 147 emerged from quieter conditions, it might never have had them to begin with. But this raises more questions. How could two galaxies so close in size and structure have such different origins? Some astronomers speculate that NGC 147 might be the remnant of a larger galaxy that was torn apart, leaving behind only its core, a core that never hosted clusters. Meanwhile, NGC 185 could have formed more traditionally, holding onto its clusters as it evolved. The mystery deepens when we consider dark matter. Globular clusters often orbit in a galaxy's outer halo, where dark matter's gravity keeps them anchored. If NGC 147 has an unusual dark matter distribution, say a weaker or more diffuse halo, its clusters could have drifted away over time. Observations hint that NGC 147 stars move more sluggishly than those in NGC 185, suggesting it might have less dark matter holding it together. Without that invisible scaffolding, its clusters could have escaped into intergalactic space. What makes this puzzle so compelling is that it challenges our assumptions about how dwarf galaxies evolve. If two nearly identical galaxies can have such different histories, what does that say about the forces shaping them? NGC 147 and NGC 185 are like siblings raised in the same neighborhood who turned out completely different, one holding onto its ancient heirlooms, the other leaving them behind. Studying these twins gives astronomers a rare chance to isolate what factors really determine a galaxy's fate. Is it the environment, the initial conditions, or just cosmic luck? As we move forward in our journey through the local group's strangest objects, remember that even the smallest galaxies can hold the biggest surprises. Up next, we'll encounter a galaxy connected to Andromeda by a bridge of stars, a ghostly remnant of a long-forgotten collision. Now, let's turn our attention to a celestial spectacle that looks more like a work of art than an astronomical phenomenon. Between Andromeda and one of its smaller companions, Andromeda 24, stretches a shimmering arc of stars, a ghostly bridge that tells a violent tale of cosmic destruction and rebirth. This isn't just a random scattering of stars, it's evidence of a dwarf galaxy torn apart, its remains strung across space like pearls on a necklace. What makes this bridge so special? Unlike the smooth, symmetrical structures we often see in galaxies, this one is messy and uneven, a clear sign of gravitational chaos. When a smaller galaxy ventures too close to a giant like Andromeda, the larger galaxy's tidal forces, think of them as cosmic versions of the moon's pull on Earth's oceans, can stretch the intruder like taffy. Over time, stars are yanked from their orbits, forming long, looping streams. In this case, Andromeda 24 seems to be the survivor of that encounter, while the bridge is what's left of its unfortunate neighbor. The stars in this ribbon aren't just drifting aimlessly, they're moving in a coordinated flow, tracing the path of their doomed parent galaxy. But here's where it gets even stranger. Unlike typical tidal streams, which fade as they disperse, this bridge is unusually dense, packed with stars that somehow clung together despite the violence. One explanation is that the original dwarf galaxy was exceptionally sturdy, perhaps held tight by an above-average amount of dark matter. When Andromeda's gravity began shredding it, the dark matter's grip might have slowed the disruption, leaving this densely populated bridge behind. Another possibility is that we're seeing not one but multiple episodes of destruction, a series of collisions that piled stars into this narrow band. The bridge also offers a rare opportunity to study Andromeda's hidden structure. By mapping how the stars move within it, astronomers can reverse engineer Andromeda's gravitational field, revealing where its invisible dark matter halo is strongest. Surprisingly, the bridge's shape doesn't perfectly match predictions, hinting that Andromeda's halo might be lumpier or more elongated than we thought. This could mean that Andromeda has a more chaotic merger history than our Milky Way, with multiple galaxies already digested into its form. What's next for Andromeda 24 and its starry bridge? Over millions of years, the bridge will likely dissolve, its stars blending into Andromeda's outer halo. But for now, it stands as a stunning reminder that galaxies aren't static islands, they're dynamic, ever-changing beasts growing by consuming their smaller neighbors. Up next, we'll explore a galaxy caught in the act of transformation, one that's shedding its old identity as it plunges toward the local group's crowded core. Now, let's shift our gaze to a small but fascinating galaxy undergoing a dramatic makeover. The DDO 210, a seemingly unassuming dwarf galaxy, is caught in the middle of a cosmic identity crisis, slowly morphing from a loose, irregular blob into a more structured, spheroidal shape. This transformation isn't just a random phase, it's a direct result of the galaxy's perilous journey toward the heart of the local group, where gravitational forces are reshaping its very existence. What makes DDO 210 stand out is its unusual combination of features. Unlike many dwarf galaxies, which are either clearly irregular or fully spheroidal, this one is caught in between. It still holds onto large reservoirs of gas, the raw material for star formation, giving it a somewhat messy appearance. But at the same time, its stars are beginning to settle into a more rounded, organized structure, as if the galaxy can't decide whether to cling to its youthful chaos or embrace the orderly fate of its older siblings. The key to this transformation lies in its motion. DDO 210 isn't just drifting aimlessly through space, it's falling toward the local group's center, where giants like the Milky Way and Andromeda dominate. As it gets closer, the gravitational pull from these larger galaxies starts to strip away its outer layers, particularly the gas that fuels star formation. Think of it like a comet venturing too close to the sun. Its icy tail gets blown away by solar winds. Similarly, DDO 210's gas is being peeled off, leaving its stars more exposed and allowing gravity to mold them into a smoother shape. But here's where things get even more intriguing. Unlike some dwarfs that lose their gas quickly and become dead spheroidal galaxies, DDO 210 is holding on tighter than expected. Its gas isn't being stripped all at once. Instead, the process is slow and uneven, creating pockets where star formation still flickers to life. This suggests that the galaxy might have a bit more resilience, perhaps due to its original gas content or the angle at which it's falling into the local group's gravitational well. Astronomers are particularly interested in DDO 210 because it's like a snapshot of a critical phase in galactic evolution, one that many small galaxies go through but rarely while we're watching. By studying its structure, motion, and remaining gas, researchers can piece together how larger galaxies like the Milky Way grew by absorbing and reshaping smaller ones. The galaxy's transitional state also gives clues about the environment of the local group itself, revealing how the pull of dark matter and the interactions between galaxies shape their destinies. What does the future hold for DDO 210? If it continues on its current path, it will likely lose all its gas, and its stars will settle into a tight, spheroidal shape, joining the ranks of so-called dwarf spheroidal galaxies. But for now, it's a living laboratory showing us the forces that sculpt galaxies over cosmic time. Up next, we'll examine another enigma, a dwarf galaxy whose very location has sparked debates among astronomers, challenging our assumptions about the local group's boundaries. Now, let's turn our attention to a cosmic mystery that has astronomers scratching their heads: the puzzling case of Andromeda 22. This faint dwarf galaxy poses a simple yet baffling question. Is it truly a neighbor of Andromeda, or just an optical illusion, a distant galaxy that happens to appear nearby in our telescopes? The answer isn't as straightforward as you might think, and the debate hinges on one crucial measurement: redshift. Think of redshift as a galaxy's cosmic fingerprint. When light from a galaxy stretches as it travels through the expanding universe, shifting toward the red end of the spectrum, it tells us how far away the galaxy is. Normally, this measurement lets astronomers confidently place galaxies in space. But Andromeda 22 has thrown a wrench in that system. Initial redshift readings suggested it was much farther away than Andromeda's other satellite galaxies, implying it wasn't actually bound to Andromeda's gravity. That would make it an imposter, a background object merely pretending to be part of the local group. However, later observations muddied the waters. Some redshift measurements aligned with Andromeda's known satellites, placing Andromeda 22 right where it should be as a genuine companion. So why the discrepancy? One possibility involves the galaxy's faintness. Being an ultra-diffuse dwarf, its light is incredibly dim, making precise redshift measurements difficult. The readings might have been contaminated by foreground stars in our own Milky Way or by quirks in the telescope's calibration. Another theory suggests Andromeda 22 could be moving unusually fast within Andromeda's gravitational grip, skewing its apparent redshift. The stakes are higher than they seem. If Andromeda 22 is confirmed as an Andromeda satellite, it challenges our models of how dwarf galaxies form and orbit. Its unusual position and motion could hint at past interactions with Andromeda, perhaps a violent encounter that flung it into its current path. On the other hand, if it's a distant background galaxy, it raises questions about how many other faint objects we might be misclassifying in our cosmic neighborhood. This debate isn't just academic, it's reshaping how we map the local group. Every dwarf galaxy we identify helps us piece together the history of galactic evolution, from star formation to dark matter distribution. Misplacing even one galaxy can throw off our understanding of the whole system. That's why astronomers are pushing for better observations, using more sensitive instruments to nail down Andromeda 22's true nature once and for all. So where does this leave us? For now, Andromeda 22 remains a celestial riddle, a reminder that even in our own galactic backyard, the universe keeps secrets. Whether it's a rogue satellite or a distant stranger, its story is far from over. Next up, we'll explore another dwarf galaxy with its own set of surprises, one where the stars seem to huddle together in a way that defies expectations. Now, let's shift our gaze to another cosmic oddity, the Antlia dwarf, a tiny galaxy with a peculiar secret. Unlike most dwarf galaxies where stars are scattered far and wide, Antlia's stars seem to cluster tightly near its core, almost as if they're crouching together for safety. This unusual arrangement has astronomers asking, what's forcing these stars into such a compact formation? The answer might lie in the invisible grip of dark matter. Most dwarf galaxies follow a predictable pattern. Their stars are spread out in a loose, fluffy halo with a gentle decline in density as you move outward. But Antlia defies this norm. Observations show its stars are concentrated in a dense central clump, with very few venturing into the outskirts. It's as if the galaxy's outer regions have been stripped away, leaving only the core behind. So what could cause such a stark difference? One leading theory points to dark matter, the mysterious, invisible substance that makes up most of a galaxy's mass. In typical dwarfs, dark matter forms a sprawling, diffuse halo that cradles the stars. But Antlia's dark matter might be arranged differently. Some models suggest it could have a chord profile, meaning its dark matter is piled up in the center rather than spread evenly. This dense central mass would act like a gravitational anchor, pulling stars inward and explaining why they huddle so close. But there's a twist. Other dwarf galaxies with similar dark matter halos don't show this extreme central clustering. So why is Antlia special? One possibility is its turbulent past. If Antlia had a close encounter with a larger galaxy, perhaps the Milky Way or another neighbor, that interaction could have ripped away its outer stars, leaving only the tightly bound core behind. Alternatively, Antlia might have simply formed this way, born with an unusually high concentration of dark matter at its heart. The implications are profound. If Antlia's dark matter is indeed concentrated in its center, it challenges some of our standard models of galaxy formation. Most simulations predict dark matter halos should be fluffy and extended, not compact. Antlia's defiance could mean our understanding of dark matter's behavior needs tweaking, or that we're missing a key piece of the puzzle, like unseen interactions with other galaxies. What's certain is that Antlia's crouching stars are more than just a curiosity. They're a clue to the hidden forces shaping galaxies, a reminder that even the smallest cosmic objects can hold big surprises. Up next, we'll dive into another enigma, a dwarf galaxy with not one, but two distinct stellar cores, as if frozen mid-collision. Now let's unravel the mystery of Andromeda 25, a dwarf galaxy with what appears to be a cosmic identity crisis. Picture this: most galaxies have a single, well-defined core where stars cluster around a central point. But Andromeda 25 breaks the mold by flaunting not one, but two bright stellar cores, as if it can't decide who it wants to be. This bizarre double nucleus has astronomers scratching their heads, wondering if we're witnessing a galactic merger frozen in time. When astronomers first spotted Andromeda 25's twin cores, the immediate suspicion was that two smaller galaxies had begun colliding but got stuck midway. Think of it like two cars crashing in slow motion, only instead of metal crumpling, you've got stars and dark matter threading together in a gravitational dance. The two cores are separated by just a few thousand light-years, close enough to feel each other's pull but far enough to retain their individual identities. This delicate balance suggests the merger isn't complete yet, giving us a rare snapshot of a process that usually happens too quickly to observe in detail. But here's where it gets even stranger. Normally, when galaxies merge, their cores spiral toward each other, eventually smashing together to form a single, larger nucleus. Yet Andromeda 25's cores seem stubbornly resistant to this fate. Some researchers propose that dark matter might be playing referee here, creating a sort of gravitational buffer that keeps the two cores apart. Alternatively, the galaxies involved might have been unusually dense, making it harder for their cores to fully merge. Either way, this standoff challenges our assumptions about how galactic collisions play out. What makes Andromeda 25 especially valuable is its location. It's orbiting Andromeda, our nearest giant galactic neighbor. That proximity gives us a front-row seat to study its split personality up close. By measuring the motion of stars in each core, astronomers can piece together the galaxy's history. For instance, if the stars in one core are moving differently than those in the other, it could hint at their original identities before the merger began. The implications stretch beyond this one oddball galaxy. If Andromeda 25 is indeed a paused merger, it could help explain why some galaxies in the universe have clumpy or irregular structures. Perhaps many of them started as pairs like this, caught in a slow-motion collision we're only now learning to recognize. It also raises questions about how often dwarf galaxies merge and whether these events might seed the growth of larger galaxies over cosmic time. So while Andromeda 25 might seem like an anomaly, it's really a cosmic lesson in disguise. Its split personality offers a glimpse into the chaotic yet beautiful processes that shape galaxies, reminding us that even in the vastness of space, some things take their sweet time. Next up, we'll explore a dwarf galaxy that stands out for the opposite reason. It's so quiet and uneventful, it might as well be a galactic ghost town. Now we turn our attention to a true cosmic recluse, the KKR-25 dwarf galaxy. While most galaxies, even the tiniest ones, show at least some flicker of star formation, KKR-25 stands apart as a silent, dormant outlier. This galaxy isn't just quiet, it's practically fossilized with no signs of young stars, glowing gas clouds, or any of the usual markers of cosmic activity. In a universe bustling with stellar nurseries and supernova explosions, KKR-25 is the equivalent of a ghost town frozen in time. What makes this galaxy so unusual is its complete lack of the ingredients needed to create new stars. Typically, dwarf galaxies, even the faintest ones, hold onto traces of hydrogen gas, the raw material for star birth, but KKR-25 appears to have been stripped clean. Its stars are exclusively old, all likely formed billions of years ago, with no recent additions to the population. This absence of gas and youthful stars suggests one of two possibilities. Either KKR-25 exhausted its fuel long ago and faded into retirement, or something, perhaps a violent encounter with a larger galaxy, siphoned away its gas, leaving it high and dry. The mystery deepens when we consider its environment. Unlike many dormant dwarfs found near massive galaxies like Andromeda or the Milky Way, KKR-25 floats in relative isolation. There's no obvious culprit nearby that could have robbed it of its gas. This raises the tantalizing question: did it lose its fuel through internal processes? Or did it wander too close to another galaxy in the distant past, only to be flung back into lonely exile? Astronomers are particularly intrigued by galaxies like KKR-25 because they challenge our understanding of how dwarf galaxies evolve. Most models predict that small galaxies should either be actively forming stars or show signs of recent activity, but KKR-25 defies expectations. Its extreme passivity makes it a key piece in the puzzle of galactic life cycles. By studying it, researchers hope to uncover why some dwarfs shut down early while others keep churning out stars for eons. One leading theory is that reionization, the epoch when the first stars flooded the universe with ultraviolet light, might have played a role. In this scenario, KKR-25 could be a relic from that ancient era, a galaxy whose gas was heated and stripped away before it had a chance to build many stars. Alternatively, its dark matter halo might have been too sparse to hold onto its gas, allowing it to leak away over time. Both ideas highlight how delicate the balance is between a galaxy's internal properties and its cosmic surroundings. The rarity of galaxies like KKR-25 also makes them invaluable. They're cosmic dead ends, offering snapshots of how galaxies can fade into obscurity. If we can find more of them, we might start to piece together how common such early quenching really is, and whether it's a natural phase for some dwarfs or the result of specific catastrophic events. For now, KKR-25 remains an enigma, a silent witness to processes we're only beginning to understand. Its existence reminds us that the local group isn't just a collection of vibrant, star-forming galaxies. It's also home to these forgotten outliers, galaxies that burned out long before their neighbors. Next, we'll dive into another oddity, a dwarf galaxy whose shape has been warped beyond recognition, twisted by the relentless tides of its giant neighbor. Now, let's shift our focus to another cosmic oddity, the Andromeda 26 dwarf galaxy, a celestial underdog whose very shape tells a story of gravitational bullying. Unlike the dormant KKR-25, Andromeda 26 is very much alive, but it's been dramatically reshaped by the overwhelming influence of its colossal neighbor, the Andromeda Galaxy. What makes Andromeda 26 stand out is its unmistakably warped disk. Most dwarf galaxies, even those orbiting giants, maintain a roughly spherical or slightly flattened shape. But this one looks like it's been twisted by invisible hands, its stars and gas stretched into a lopsided, almost contorted structure. The culprit, tidal forces, the relentless gravitational tug of war between Andromeda 26 and its far more massive host. Simulations of this cosmic dance reveal just how violent these interactions can be. As the dwarf galaxy orbits Andromeda, the difference in gravity between its near and far sides, known as tidal stretching, pulls it apart. Over time, this stretching warps the galaxy's disk, bending it out of shape like a piece of taffy. In some cases, these forces can even strip away stars and gas, leaving behind long, shimmering trails known as tidal streams. But Andromeda 26 hasn't been completely torn apart, at least not yet. Instead, its distorted shape serves as a snapshot of a galaxy caught in the middle of a cosmic transformation. The oddest part, this warping isn't uniform. Some regions of Andromeda 26 appear more twisted than others, suggesting it didn't just make a single, simple pass near Andromeda. Instead, it's likely been subjected to multiple close encounters, each one bending it further out of shape. Computer models show that its current form matches what we'd expect if it's been orbiting Andromeda for billions of years, gradually getting reshaped with every lap. But why does this matter? Because Andromeda 26 isn't just a curiosity, it's a living lab for studying how small galaxies evolve under extreme conditions. Most dwarf galaxies in the local group are either isolated or locked in stable orbits, but Andromeda 26 gives us a front-row seat to the destructive power of tidal forces. By studying its warped structure, astronomers can refine their models of how galaxies interact, improving predictions about the fate of other dwarfs, including those orbiting our own Milky Way. One particularly intriguing detail is the galaxy's rotation. In most spirals, stars and gas move in a predictable, orderly fashion. But in Andromeda 26, the warping has disturbed this motion, creating chaotic orbits that further hint at its violent past. Some stars might even be in the process of being ejected, destined to join the halo of Andromeda as free-floating strays. The broader implication here is that Andromeda 26 is a preview of what could happen to other satellite galaxies, even our own Magellanic clouds, given enough time. As the Milky Way and Andromeda inch closer to their eventual collision, tidal forces will only intensify, and more dwarfs may find themselves twisted, stretched, or even shredded. What's next for Andromeda 26? Current simulations suggest two possible futures. If its orbit keeps it at a safe distance, it might stabilize, its warped disk becoming a permanent feature. But if it ventures too close again, it could be torn apart entirely, its stars scattered into Andromeda's halo, a ghostly reminder of a galaxy that once was. Up next, we'll examine a dwarf galaxy that's not just being shaped by its environment, it's actively fleeing from it. Stay tuned for the story of Andromeda 25, a galaxy moving so fast it might be making a break for freedom. Now, let's turn our attention to a galactic escape artist, the Ultra-86 galaxy, where stars aren't just twinkling peacefully but are racing away at breakneck speeds. This peculiar dwarf irregular galaxy hosts what astronomers call runaway stars, celestial renegades that have been violently ejected from their birthplace, streaking across space like cosmic outlaws. What makes these stars so extraordinary is their sheer velocity. While most stars move in predictable orbits around their galaxy's center, these outliers are zooming away fast enough to escape Ultra-86 entirely. Their speeds can exceed hundreds of kilometers per second, so fast that they'll eventually leave their home galaxy behind, destined to wander the void alone. So how do stars reach such extreme velocities? There are two leading theories, both as dramatic as they sound. The first involves supernova, the explosive deaths of massive stars. In binary star systems where two stars orbit each other, if one goes supernova, the sudden loss of mass can fling the surviving companion outward like a slingshot. Imagine holding hands with a friend who suddenly vanishes mid-spin. You'd go flying. That's essentially what happens to these stars. The second theory points to black holes specifically, the supermassive black holes lurking in galactic centers. If a star ventures too close to such a black hole, the intense gravitational interaction can hurl it away at unbelievable speeds. In some cases, a close encounter between two binary stars and a black hole might result in one star being captured while the other is ejected at high velocity. It's a cosmic game of gravitational pinball, with stars as the balls. UGCA-86 is an ideal laboratory for studying these runaway stars because it's relatively isolated, meaning there's less interference from neighboring galaxies. This isolation makes it easier to trace the origins of these high-velocity stars and determine which mechanism, supernova or black hole interactions, is responsible for their escape. Astronomers have used advanced telescopes to track their trajectories, and the data suggests both processes might be at play. Some runaways appear to originate from dense star-forming regions where supernovae are common, while others seem to have been launched from the galaxy's core, hinting at black hole involvement. But why should we care about stars that abandon their galaxies? These runaways offer a unique window into the violent processes shaping galaxies. By studying their speeds and paths, astronomers can infer the conditions that expelled them, like the energy of ancient supernova or the dynamics of black hole encounters. They also serve as cosmic probes. As these stars travel through intergalactic space, they carry clues about their home galaxy's composition, helping us map the otherwise invisible structure of the universe. There's also the tantalizing possibility that some runaway stars might host planets. If these worlds survived the violent ejection process, they'd become interstellar nomads orbiting stars untethered to any galaxy. Imagine a planet bathed in eternal night, its sky devoid of neighboring stars where the only light comes from its rogue sun. It's a bleak but fascinating scenario, and UGCA-86's runaways could help us assess how common such lonely worlds might be. One particularly intriguing runaway in UGCA-86, dubbed the Fugitive, has astronomers buzzing. Observations suggest it was launched by a supernova roughly 5 million years ago, and its trajectory indicates it might have once belonged to a binary system. The Fugitive is now racing toward the outskirts of the local group, and if it maintains its speed, it'll eventually leave our galactic neighborhood entirely. The broader implication here is that runaway stars aren't just oddities, they're proof of the dynamic, sometimes chaotic nature of galaxies. Every high-velocity star tells a story of cosmic violence, whether it's the explosive death of a stellar companion or a perilous dance with a black hole. And UGCA-86, with its abundance of these renegades, serves as a vivid reminder that even in the vastness of space, nothing stays still for long. Next, we'll explore another dwarf galaxy with a bizarre history, one that might not have formed the way we thought. Stay tuned for the strange case of Andromeda 23, where nothing is quite as it seems. Now, let's unravel a cosmic mystery hiding in plain sight. Andromeda 23, a dwarf galaxy that might be an imposter. Unlike most galaxies, which form from primordial gas collapsing under gravity, this one could be something far more unusual, a tidal dwarf born from the wreckage of a violent galactic collision. Picture this: two massive galaxies slam into each other, their gravitational forces tearing streams of gas and stars loose like cosmic confetti. Most of this debris eventually falls back into the larger galaxies or disperses into the void, but sometimes, under just the right conditions, a clump of this material collapses and forms a new, smaller galaxy. That's the tidal dwarf hypothesis, and Andromeda 23 fits the profile perfectly. So what makes astronomers suspect this dwarf didn't form the traditional way? First, its chemistry. Most primordial galaxies have stars with low metallicity, meaning they're made of hydrogen and helium, the universe's original elements. But Andromeda 23 stars are surprisingly metal-rich, suggesting they formed from gas already enriched by earlier generations of stars. That's a telltale sign it's recycled material, not pristine cosmic fuel. Then there's its location. This dwarf sits along a faint stream of stars, linking it to Andromeda's main disk, a ghostly trail that could be debris from the collision that birthed it. Simulations show that when galaxies merge, such streams often spawn tidal dwarfs along their lengths, like beads on a string. Andromeda 23 might be one of those beads, a celestial afterthought from a long-ago cosmic crash. The most compelling evidence, though, comes from its movement. Tidal dwarfs don't orbit their parent galaxies neatly. Instead, they often follow chaotic, elongated paths that reflect their violent origins. Andromeda 23's orbit is just that erratic, as if it's still carrying the momentum of the collision that created it. But why does this matter? If confirmed, Andromeda 23 would challenge our understanding of how galaxies form. Traditionally, we've classified galaxies by their size and shape, assuming they all arose from similar processes. But tidal dwarfs blur those categories, proving galaxies can emerge from destruction as easily as creation. They're cosmic phoenixes rising from the ashes of larger galaxies' collisions. There's also a practical reason to study them. Tidal dwarfs are laboratories for star formation. The gas in these galaxies has been violently stirred, creating dense pockets where stars can ignite rapidly. By observing Andromeda 23's stellar populations, astronomers can learn how turbulence affects star birth, an insight that applies to galaxies across the universe. Of course, not everyone agrees this dwarf is a tidal remnant. Some argue it could be a traditional galaxy that simply passed too close to Andromeda, getting stretched into its odd shape. But the metal-rich stars and chaotic orbit make a strong case for the collision theory. Future telescopes, like the upcoming Nancy Grace Roman Space Telescope, might settle the debate by mapping the dwarf's structure in unprecedented detail. One thing's certain, Andromeda 23 forces us to rethink what a galaxy can be. It might not have formed in the quiet darkness of the early universe, but in the chaos of a galactic wreck, a testament to the fact that even in space, beauty can emerge from catastrophe. Next, we'll examine a galaxy that's fading into obscurity, its star formation slowing to a whisper. Stay tuned for the enigmatic story of DDO 216, where the lights are dimming, but not without a fight. Now, let's turn our attention to a galaxy entering its twilight years, DDO 216, a small but fascinating system where the lights of new stars are slowly flickering out. Unlike the violent births we've seen in other galaxies, this one tells a quieter, more melancholic story of cosmic decline. At first glance, DDO 216 might seem unremarkable, a modest, irregular dwarf galaxy drifting through the local group. But look closer and you'll notice something unsettling. Its star formation rate has plummeted to a mere whisper, with fewer and fewer young stars igniting across its gas clouds. This isn't just a slow phase, it's a galaxy running out of fuel, and the culprit might be lurking in the space around it. The leading theory points to the local group's so-called hot halo, a vast, invisible shroud of superheated gas enveloping our galactic neighborhood. As DDO 216 moves through this searing environment, the intense heat and pressure could be stripping away its cold, star-forming gas, like a ship losing cargo in a storm. Without this vital material, the galaxy can't replenish its stellar nurseries, leaving it to fade into obscurity. Evidence for this comes from its uneven gas distribution. Observations show its remaining hydrogen is clumped oddly, as if chunks have been torn away. Meanwhile, the galaxy's outer regions appear especially depleted, a telltale sign of ram pressure stripping, the same process that occurs when a galaxy plunges through a galaxy cluster's hot gas. But here's the twist: DDO 216 isn't in a dense cluster. It's relatively isolated, suggesting the local group's diffuse halo alone might be enough to suffocate a small galaxy over time. There's another clue in its stellar populations. Most star-forming galaxies have a mix of young, blue stars and older, redder ones, but in DDO 216 the balance is skewed. The few young stars it has are clustered near its core, where gas might still cling on, while its outer edges are dominated by aging stars, like a city where the outskirts are abandoned and only the downtown still flickers with life. This decline isn't just academic. It's a preview of what might happen to many small galaxies as the local group evolves. Over billions of years, gravitational interactions and environmental effects could leave our neighborhood dotted with quenched dwarf galaxies that have exhausted their gas and ceased forming stars. DDO 216 might be one of the first to cross that threshold, offering astronomers a real-time glimpse of how galaxies die. But here's the twist: it's not going quietly. Even as its star formation dwindles, there are pockets of resistance. Some regions show faint bursts of activity, as if the galaxy is making one last stand. These could be caused by minor mergers or turbulence stirring up leftover gas, proving that even in decline, nature fights back. The irony: DDO 216's struggle teaches us more about galaxy evolution than its vibrant counterparts. By studying how it loses gas and resists fading, we refine our models of galactic life cycles not just for dwarfs, but for giants like the Milky Way, which might one day face a similar fate. Up next, we'll shift from a fading light to a ghostly presence, the Milky Way's most enigmatic satellite, Crater 2. This shadowy dwarf defies expectations with its bizarre combination of size and dimness, earning it the title of the local group's greatest ghost. Stay tuned. Now, let's unravel the mystery of Andromeda 28, a galaxy wrapped in its own ghostly shroud. Unlike the fading embers of DDO 216, this satellite of Andromeda tells a story of cosmic violence, a relic of destruction that lingers like a phantom in the night sky. At first glance, Andromeda 28 seems unassuming, a faint smudge on the edge of its massive host, but peer deeper and the truth emerges. This dwarf galaxy is cloaked in an enormous, eerie halo of stars, a stellar envelope stretching an astonishing 15,000 light-years. To put that in perspective, that's nearly 1/6 the diameter of the entire Milky Way. Yet, despite its vast size, this halo is so dim it nearly vanishes against the blackness of space, earning it the nickname, the Ghost of Andromeda. So, how did this eerie structure form? The leading theory is as dramatic as it gets: cannibalism. Astronomers believe this halo is the mangled remains of a smaller dwarf galaxy that strayed too close to Andromeda's gravitational grasp. Over billions of years, Andromeda's tides ripped the victim apart, scattering its stars into a vast, diffuse cloud. What we see today isn't a living galaxy but a corpse, its stars orbiting in a chaotic, elongated swarm, still bound by gravity but forever altered. The evidence for this violent past is written in the stars themselves. Unlike the tight, orderly orbits of stars in intact galaxies, Andromeda 28's halo stars move in wild, unpredictable paths. Some race toward us, others away, like debris ejected from a collision. Their chemical makeup also tells a tale. These stars are older and metal-poor, typical of ancient dwarf galaxies that formed in the early universe. It's as if we're looking at the fossilized remains of one of the local group's earliest inhabitants. But here's where it gets even stranger. Most cannibalized dwarfs dissolve completely, their stars merging seamlessly into their host galaxy's halo. Yet Andromeda 28's ghostly envelope persists, a coherent structure defying total destruction. This suggests the original dwarf was unusually dense or rich in dark matter, its gravitational glue strong enough to keep some semblance of shape even after annihilation. It's a cosmic paradox, a galaxy that's both dead and not quite gone. What makes this discovery so valuable is its rarity. While computer simulations predict such stellar halos should be common around large galaxies, few have been observed in such detail. Andromeda 28 gives us a front-row seat to the aftermath of galactic cannibalism, a process that shaped giants like Andromeda and the Milky Way. In fact, our own galaxy likely wears similar ghostly halos, the remnants of dwarfs it consumed over billions of years. The implications stretch beyond a single galactic murder mystery. By studying Andromeda 28, astronomers refine their models of how galaxies grow. Galactic mergers aren't just dramatic events, they're the architects of cosmic structure, building larger galaxies piece by piece. This phantom halo is a snapshot of that process frozen in time, a reminder that even the grandest galaxies owe their existence to countless smaller acts of destruction. And yet, for all we've learned, questions remain. Why did this dwarf's halo survive when others dissolved? Could dark matter be the key, or is there another force at work? Every answer peels back another layer of the local group's hidden history. Up next, we confront a different kind of enigma, Crater 2, a galactic ghost so faint and sprawling it redefines what we thought possible for dwarf galaxies. Stay with us as we step into the shadows of the local group's most elusive specter. Now we turn our gaze to one of the most puzzling residents of the local group, Crater 2, a phantom lurking right on our cosmic doorstep. This ultra-faint dwarf galaxy is so elusive, so bizarrely out of place, that it challenges everything we thought we knew about galactic evolution. Crater 2 isn't just dim. It's spectrally dim, a shadow of a galaxy, stretching nearly 7,000 light-years across but emitting less light than a single bright star. If you were to stand on a planet within it, the night sky would be almost pitch black, with only a sparse sprinkling of ancient stars overhead. This makes it one of the largest yet faintest galaxies ever discovered, a contradiction so extreme it's earned the nickname, the ghost of the local group. So, how does something so massive remain so invisible? The answer lies in its stars, old, red, and incredibly spread out. Most dwarf galaxies pack their stars into dense clusters, but Crater 2's stellar population is diffuse, like handfuls of sand tossed across a football field. Its surface brightness is 100 times fainter than the Milky Way's darkest patches, making it nearly undetectable until advanced telescopes like the Oddities survey in Chile peeled back the shadows in 2016. But the real mystery isn't just its faintness, it's the fact that Crater 2 shouldn't exist in its current form. Standard models predict that galaxies this large should have either collapsed into tighter shapes or been torn apart by the Milky Way's gravity long ago. Yet here it is, a wispy giant defiantly holding its ground about 380,000 light-years from Earth. This has led to two competing theories, each more intriguing than the last. The first possibility, Crater 2 is a failed dwarf born with too little dark matter to condense properly. Normally, dark matter acts as cosmic scaffolding, pulling stars together into coherent structures. Without enough of it, a galaxy might expand into this ghostly state, never achieving the density of its peers. But here's the twist: Crater 2's stars move faster than expected for such a dim object, hinting at more dark matter, not less. That contradiction has astronomers scratching their heads. The second theory is even wilder. Crater 2 might be the remnant of a high-speed collision, a dwarf galaxy that once orbited the Milky Way but was slingshot outward by a close encounter. The gravitational kick could have stretched it into its current diffuse state while leaving its stars just bound enough to avoid dispersing entirely. Supporting this, Crater 2 shares a trajectory with several globular clusters, suggesting they might all be survivors of the same ancient disruption. What makes this ghost so scientifically valuable is its uniqueness. Most ultra-faint dwarfs are tiny, but Crater 2's size implies a different formation path, one that could rewrite our understanding of galactic survival. Its existence suggests there might be an entire population of similar, stealth galaxies hiding in plain sight, overlooked because they don't fit traditional search parameters. The implications ripple far beyond our local group. If Crater 2 formed through processes we don't yet understand, similar ghosts could lurk around other galaxies, silently reshaping our models of cosmic structure. It's a humbling reminder that even in our own backyard, the universe still holds breathtaking surprises. And with that, we've reached the end of our journey through the 50 strangest objects in the local group. From cannibalized halos to stellar phantoms, these cosmic oddities prove that the universe is far weirder and far more wonderful than we ever imagined. As we wrap up this journey through the cosmic oddities of our galactic neighborhood, let's take a moment to reflect on just how extraordinary these 50 objects truly are. From Andromeda's double nucleus to Crater 2's ghostly presence, each one defies expectations in ways that leave astronomers both baffled and exhilarated. These aren't just curiosities, they're cosmic rebels that force us to rethink the rules of galaxy formation, dark matter, and stellar evolution. Think about it. The local group was supposed to be familiar territory, our cosmic backyard where the textbooks had all the answers. But time and again, we've stumbled upon puzzles that shake the foundation of what we thought we knew. Why does the Triangulum galaxy lack dark matter? How did Leo I end up with a halo rivaling the Milky Ways? What keeps the Fermi Bubbles pumping out gamma rays long after their suspected creation? These aren't minor gaps in knowledge, they're glaring signs that the universe still has secrets to spill. And here's the thrilling part. If 50 strange objects can hide in plain sight within our own galactic neighborhood, imagine what else might be lurking just beyond our current telescope's reach. Could there be more ultra-diffuse ghosts like Crater 2 drifting undetected? Might some dwarf galaxies be hiding entirely new classes of dark matter? Every oddity we've explored today isn't just a mystery, it's a roadmap to discoveries waiting to happen. Now, we'd love to hear from you. Which of these cosmic enigmas caught your imagination the most? Was it the Magellanic stream's tangled origins, or perhaps Andromeda Roman 19 whisper-thin stars? Drop your favorite in the comments below. We're just as curious as you are. And if you've enjoyed this deep dive into the local group's weirdest residents, don't forget to subscribe and hit that notification bell. The universe is vast, strange, and endlessly surprising, and we're just getting started unraveling its wonders together. Until next time, keep looking up because who knows what other cosmic ghosts might be watching back.